typically join. So we need to, I assume by the end of 2 o'clock, there'll still be around 80 or 90 people on, and it's a good time to remind people of the post survey.
Hillary's here, so maybe she can do that too.
Yeah, so I don't know when she joined, but I think for this first hour, when we're going over homeworks and things like that, I've noticed that we don't have the full complement. People tend to peak out around 11 or 12. And so we should make an announcement. I have to leave at 10:30, but we should make an announcement later about ensuring that we have good feedback from the post survey. There's the link that Hillary just posted. We had quite a bit of pre-course pre-assessment. I think it was over 90, which is pretty good.
And I just like to say, it's not too late to do it. Don't be discouraged. If you can just rewind and pretend it's last week, and so think about, you're probably keenly aware of what you didn't know last week at this point. So if you want to go back and pretend that and be in that time period, you can still do the pre-survey.
Okay, fair enough. And just a reminder, there is another week basically when the OSL instances will still be available. So the homework should be completed as soon as you can get it done, and preferably well before the end of next week, but Friday is the cutoff next week. And let's see, there was another thing. Oh, the Docker file. Looks like good progress is being made. I don't think France is on yet, but I know they're getting that ready. We're trying to decide where to put it so that people can just easily download it. My personal preference would be to put it in the GeoSync area, since it's not just ICE software, it's a bunch of other things as well. And it should also, I think, be made available by ASF directly. But, or UNAVCO could host it. So I guess we have to make a decision on that at some point. But we'll make it clear how you can get it.
Task for Becca, maybe.
I'm sorry, I missed that. What, Gareth?
You could add it to Becca's to-do list.
Well, Becca is
might
now,
finish. Is she
yeah,
free?
she's gone for this week. I don't know if she's coming back. Her internship at UNAVCO, I guess, ends at some point.
Yeah,
Maybe,
I was joking.
I know you were. Maybe Melissa knows exactly.
I think she's got a few things that she's got to wrap up for the workshop last week, because she assisted with that too. But yeah, I think she's scheduled to be done September 1st.
Yeah. But I'm sure she'd be happy to help. So we'll work that out. We can probably put it in the GeoSync repository, at least for the short term, if people want to get at it quickly, and then move on to permanent home later. So let's see. Since I only have another 25 minutes, yesterday it was requested that I say a few words about the NISAR methodology. I can do that very quickly for those who might be interested. Let me just bring up my PowerPoint. There it is. All right, make that a little bit bigger. So NISAR is looking at a bunch of different science disciplines, as you probably know if you've looked at the website. We have NASA level 1 requirements, which are basically things we have to do for the mission to be considered successful in 3 main areas, 4 to some degree, but mostly 3 main areas. Dynamics of ice, measuring the ice sheets and mountain glaciers, sort of continuously get time series of their variability over the life of the mission so that we can look at questions of climate forcing, climate change, and effects on sea level rise. Also in the ecosystems area, using our long wavelength global observations, we're looking at changes in reflectivity that can be a proxy for changes in biomass in forests, wetlands, agriculture, and trying to understand that change and how it relates to the carbon cycle. And in this, in the solid earth area, we are, of course, measuring earthquakes, volcanoes, landslides, such as you're studying in this class to understand risks. And because of our persistent day-night, all-weather kind of capability, lots of people are using SAR data for disaster monitoring. Here's an example on the bottom left of tracking a fire. And we have level 1 requirements to sort of explore the operational value of a mission like NISAR, which is taking data pretty much everywhere it can on a regular basis and making that available at high level. India, our partner in this mission, has a lot of other objectives that are mostly regionally focused, looking at their mangroves and other coastline phenomena, bathymetry out in the ocean through basically from looking at the changes in reflectivity due to the local water topography and how that is reflecting the subsurface bathymetry and other things. So as you probably know, we have L-band and S-band. L-band is provided by NASA, S-band is provided by India. And this gives us a unique opportunity to explore the dynamic range of these two, of the phenomena that we are observing with these two wavelengths. We're using a technique called SweepSAR, which is different, very much different from the TOPS mode that is being used on Sentinel. And the value or the virtue of SweepSAR is that it allows us to get a full 240 kilometer swath at the full range and azimuth resolution with all the polarimetric modes independent of mode. Whereas for TOPS, as you heard, because of this scanning capability that they had to implement, the bursts are limited in duration, and therefore the resolution in the along track dimension is limited. They do have higher range resolution, but it does have a limited resolution in azimuth. So we have a variety of modes, different resolutions. The mission is nominally scheduled for 3 years, but as long as it's functional, it will go longer. And ISRO, in fact, in India has a 5-year requirement. So it will, even though the baseline mission for NASA is only 3 years, it's going to be at least 5 years. And of course, we have pointing and orbit control for interferometry, as we studied in this class. And one of the main advantages of the L-band system that NASA is providing is that it has a very large duty cycle. We are left looking, as we've said repeatedly over this course, and that gives us uninterrupted time series. And because of Sentinel looking at the Arctic, it allows us to focus on Antarctica. So I'm going to skip this one. This just gives some of the details. You can find these kinds of charts in various places if you're interested in these details. This is kind of interesting. We do have a very comprehensive and joint mission operations plan. We have a fixed reference observation plan that we hope to maintain effectively unchanged as much as possible throughout the life of the mission. However, we do have periodic, every 6 months, updates to this plan based on what we're learning from the mission and other community feedback. And assuming that the mission lasts 5 to 10 years, every 6 months seems like a good cadence. We're also taking urgent response requests from agencies and potentially from scientists themselves to fold into that plan. So the plans are uplinked through ISRO, who is providing the spacecraft actually. And then we execute the plan. there are two telecom systems sharing a common antenna for downlink, and the L-band data comes down to NASA stations, and it's 35 terabits of data per day, which is a fairly large volume. And the S-band data comes down through the ISRO ground stations, and that's 8 terabits per day. So quite a bit of data per day, and that's just the raw data. After processing, it amounts to many petabytes of data over the life of the mission. So SweepSAR is, I don't expect anybody to really get the details of this, because it's kind of a complex technical thing. But the point is that when we operate in SweepSAR, we transmit over the entire feed aperture, which illuminates a wide swath in the ground. And then we are tracking with digital processing techniques each of the pulses that are transmitted, that are sweeping across the swath and echoing back energy to the radar at the speed of light. So it's kind of a cool thing, but the implication for what we care about from a scientific point of view is that because there are multiple pulses within this receive window in time, we actually have to turn off the receivers. These blue bars are the receive windows. We have to turn off the receivers when we're transmitting, so as to not blow out the transmitters. Blow out the receivers while we're transmitting. So that is a problem, because it means that we have this gap periodically throughout the swath. The swath is, this wide, so we get 2 or 3 gaps across the swath, which would not be very attractive from a perspective. So what happens is, if you have a signal and you have a gap in the receive window, when you go to process it with your range reference function doing the matched filter, which you would have learned about if you looked at the SAR imaging theory notebook, you end up with a signal that is fully compressed in most of the areas, but in the area of the gap, you lose resolution down to having basically no resolved data at the middle of that gap. It gets better and better as you get closer to the edges of the gap. And it's actually a double wide issue here. So that's not great, but it's not the end of the world. The gap widths depend on the mode. I'll skip over this for now, but just to give you an idea of what that would look like, if this is a sentinel swath of 3 different, 3 subswaths with a 240 kilometer swath, which is very similar to what NISAR will have, but at L-band. If you assume our nominal global mode, the 20+5 dual pole mode, and you insist on full resolution, you would end up with gaps that look pretty wide. So this one happens to show an earthquake that is in one of our non-gap areas. But of course, by Murphy's law, anything that you care about is going to lie in this gap. And that would not be a good thing for many people. And we've had a lot of debate on the science team what to do about this. If you have, if you're willing to accept partial resolution, you can get this gap to be arbitrarily much smaller, but it's still there. Fortunately, we have a plan to operate the radar in a way where the gap location is actually moved around from one pulse to the next pulse. And there's 1,000 pulses per second or more, sometimes 2,000. So if it's moving around and you have to do the synthetic aperture processing, as you would have learned about in that notebook that I mentioned earlier, it basically smears out the gaps, adds a tiny bit of noise to the data that's basically imperceptible, and fills in the swath. So for any mode that anybody on this call cares about, the imagery, for all intents and purposes, will look like complete Sentinel images, the way we're planning to operate the radar. It doesn't work so well for quad pole, and we do have a few places in the world, India being one of them, and also agricultural areas in the Midwest where we're planning to operate in quad pole. So for quad pole data, it will look more like this. And that's kind of experimental, I would say. And we'll probably end up just filling in these holes with coarser resolution data. But for 99% of the world, or thereabouts, or maybe closer to 90, it's going to look like this. And you'll do your interferometry the way you would with TOPS, but without all of the burst related issues that TOPS presents. This is our coverage plan. The different colors here represent different radar modes. Over the US, it's going to be basically 40 megahertz bandwidth, so basically 5-meter resolution and range, 5 to 10 meters, depending on where you are in the swath. Over the ice sheets, it'll be 3 to 5 meter resolution and range. And then over the sea ice, it'll be very low resolution, like 50 meters. The rest of the world will be roughly 10 meters, 10 to 15 meters. India has a whole variety of modes that they're exercising, and this is where most of the dual L and S band observations will be acquired, as well as over parts of Antarctica. But it leads to a lot of data, and this map is occurring every 12 days on ascending and descending parts of the orbit. NISAR will process data to levels similar to what you would find in the ARIA database, interferograms. Also, we're creating this geocoded SLC stack effectively that users can do the interferometry directly from. It's just a few pictures of where we are. We've integrated pretty much everything now in the electronics. This actually is a dummy version with the hardware, the mechanical hardware integrated. We are in the process of creating this with the full suite of hardware. The launch date, because of COVID and some technical problems that we're experiencing, is a little bit uncertain at this point. It's going to be sometime in 2023, but we have had a lot of challenges with COVID, travel, and some of the technical aspects of integrating these systems. But it's coming. Any questions on that?
I have a question, Paul. Where is the data going to be hosted, and is it going to be in the cloud or just in the ASF DAC like usual?
Both. It'll be in the cloud at the ASF DAC. The ASF DAC is migrating to a cloud-based system. We may be the first, certainly the largest, although I guess Sentinel is also on the cloud. Anyway, yes, it'll be in the Amazon cloud.
Yeah, ASF operates nowadays 98% in the Amazon cloud already. So if you don't care about that, you don't have to know it. But if you like working in the cloud, it's an advantage to accessing data directly in place. And NISAR will be treated similarly. Actually, NISAR will be completely operated in the cloud. The processing. So the ingestion of data into the cloud happens very early after reception, and then all the data processing and the handoff between the project and the data center, all of that happens seamlessly in the cloud, including the distribution of data out of the cloud. Yes, you can download data as usual out of the cloud into your local machine if you want to. Just note that the data volumes are going to be very large. NISAR, I'm not sure, Paul, if you said that, will create something like 50 petabytes a year of data. And with every 12-day images, you know that already with Sentinel, if you're interested in time series analysis, data sets get large very quickly.
On the other hand, the level 2 products will be smaller, and they should be easily downloadable if they meet your needs. They'll be basically nearest neighbor interferograms. By the time we launch, we may even convince the project to do different pairs, N+1, N+2, N+3, or something like that, similar to what ARIA is doing. And we'll see how that goes. So those I think would be downloadable. There's also polarimetric products at lower resolution that should be downloadable for analysis.
Yeah,
But
some
we're-
of the things we'll do today, when Yunjun is talking about MintPy and using ARIA tools, etc., to pull data directly from the archive, stack them up, and then run them through time series analysis. This kind of workflow you should be able to do equally so for the NISAR data once they come around. So the skills you're learning today and the things you're seeing today will work in a very similar fashion with NISAR.
Right. Yeah, so the data is free and open. If you start downloading the entire world at every time step, ASF will likely throttle you. So good luck with that, but it is free. The question about resolution, yeah, I mentioned there's different modes. The azimuth resolution is fixed by the size of the antenna, which is 12 meters. So it's a 6 meter to 6 to 7 meter resolution in the long track dimension. In the range dimension, depending on the mode, it varies from 3 meters on the ground to 50 meters. The nominal global mode is around 10 to 15 meters in range.
There's a question about the geocoded SOC, Paul.
Yeah, so it's geocoded. So we're using a DEM. We're using the Copernicus DEM as our reference. And if there were no other errors like propagation, delay errors, or positioning errors and that kind of thing, these would all be perfectly co-registered to the DEM. They may be offset a little bit, but they'd be all offset the same amount. Because of the ionosphere, because of the troposphere and other errors, there will be probably a little jiggle in these images relative to their actual position. So you may need for certain applications to do some co-registration on the geocoded SLCs at some level. But that's true with any data set. So the tools should be made available for that kind of thing. And the tools exist in the software that you're studying now. Quad pole will be made available, not for every acquisition. I'm not quite sure what that means. We're operating in dual pole most of the world. There will be a quad pole mode that's operated over India in all of India and the surrounding countries on the either ascending or descending orbits. The other one, ascending or descending or ascending, will be dual pole. And then there's also a region in Alaska, I believe, where there's quad pole being taken on free orbits, and then also over the Midwest. But mostly the world will be either dual pole or, for sea ice, single pole. Yeah, so the orbital tube, depending on how you count it, is considerably better than Sentinel in the sense that its wavelength is 6 times longer at L band than at C band, and our baselines will be on the order of 2 times coarser than or worse than Sentinel's claiming. They may actually be as good by the time we fly it and make all of our adjustments. So it should be better in terms of geometric decorrelation.
Could you put that? Could you link that back to the course in the beginning, Paul? If there is not much variation in the orbital tube, it might be good for certain applications and less suitable for the other ones.
That is true. But all the ones we're studying here, I think it's good for, right?
Big for SBAS.
Yes, good for a solid Earth community or display.
So unfortunately, I really do have to go now, and I won't be back. So even though not everybody's on, I do want to say thanks to everybody for participating. Thanks to all of the instructors who are awesome. And thanks to you, Navco, for doing everything that was done to make this course a success. I hope you all enjoyed it. please do the survey, not just in terms of testing your technical knowledge, but letting us know what you think of the course, because we know it's not perfect, and we want it to be as good as it possibly can to convey the information as efficiently as possible to you. So please let us know. I'll turn it over to, I think Gareth is the de facto lead now, or you can all share it, but I'll sign off now and have a great rest of your day. Bye-bye.
Yeah. Okay, so I saw at least one person had something they wanted to show. So this is your chance. Can't remember who it was, but I'm sure you remember.
Hi, can you hear me?
Yes.
Okay, cool. So I'll try to share my screen. Can you see it?
Looks like
Yes.
Haiti.
This is not my result.
Looks good though.
Okay, it's Simone's result, but still.
And I was trying to process the same area.
We can't hear you anymore, I think, for some reason.
Did you stop talking? Oh, yeah, your voice is gone.
For some reason your audio dropped.
Did you switch your microphone off by mistake?
Wait, can you hear me?
Yeah.
Okay, great. So
And then you went away again.
Yeah.
can
Now
you
we can
hear
hear
me?
Yes.
Yeah.
Okay, let's see if it's
No
working.
sudden,
Okay,
no sudden moves.
okay, but now it's stable.
Yeah. And now it's gone again.
I don't know what's happening. Okay.
Glitches
Remove-
with the video. Maybe if you turn the video off.
It's not the video, it's just that mic is switching low. I don't know why automatically.
So now we can hear you.
Can you? But if I
So
click,
maybe if you stay sort of in this position, if you can.
yeah, let's see if it's moving. Okay. So you can see, okay, this is the result.
Yep.
Ah, you gone again.
That's really weird.
Okay, can you hear me now?
Yes,
I really don't know what's happening. Okay. My audio is not stable.
Some bad interference.
Yeah.
Maybe you should tell us everything you need to tell us while the head is in that position.
Wait, I'm. I don't know, there's something with
maybe you can try to leave and come back. Maybe that fixes it.
yes, okay.
Whoa.
Okay. In the meantime, anybody else having questions or wanting to show something? We have another 30 minutes, I think.
20, I think.
20 minutes. 18.
Or we could briefly talk about Opera if you want to, Franz, as well. So there is another project which we're kicking off at JPL in response to the Satellite Needs Working Group, where we will be generating a couple of global products and also a North America product from SAR and optical data. And a few people here on the call are also part of that team. So there will be a North America, where North America is defined as US CONUS, Alaska, then anything within Canada within 200 kilometers from the US border, and anything south of the US on the mainland up to and including Panama, where we will be generating a full resolution or at least 30-meter or better InSAR displacement product, which is a line of sight product from Sentinel as well as from NISAR. That will be generated or will be realized in the next few years, where the products also go to the ASF DAC for distribution. And then it will be a global water extent product from optical and SAR sensors, including Sentinel, NISAR, SWAT, Landsat 8, and Sentinel 2. And then there will be a global disturbance product from optical data from Landsat 8 as well as Sentinel 2 data. So the water and the disturbance product should be rolling out in the next year and a half operationally, distributed at the PODAC, which is the water DAC from NASA, as well as LPDAC, which is the land disturbance or DAC as well. So there should be more being announced at AGU, hopefully.
Magda is back.
Okay, can you hear me?
Yes.
I hope it will be stable. Okay, I try to share again. So can you see
Yes.
my noisy results? So this is what I got, and I really don't know how to improve it. I also try to make the unwrapping. So this is the result of the unwrapping. And geocoded, okay, for me it's kind of really hard to understand. And the only understandable thing, yeah, I don't remember.
Oh, it's you got something in the offset map. That's nice.
Yeah, this is the only nice thing that I got. But
no, you have unwrapped phase as well. It might not be as clean as you might want. It has a lot of unwrapping errors potentially, or little different connected components. But what you see there is the earthquake. Go back wherever it was.
This here.
Yeah. So what the issue is that you have a lot of ocean in your that's not masked out.
So maybe that when you visualize the phase, because there's a lot of noise in the phase, maybe because just at the small scale it looks more noisy than it really is. Hard to say.
I'm not sure.
But I mean, the scale is kind of, the island is big. I don't know. I was expecting to see much more nicer results like here. Okay.
Yeah, so this is filtered. I think the original thing is not filtered, but are you sure you're plotting the interferometric phase, not the SAR image phase?
Yeah.
Topo phase.
I'm not sure what's going on there, but later on you seem to have the earthquake in your geocoded unwrapped and even unwrapped. I mean that you have.
Yeah, here.
And you have connected, big connected components. So
not that big because all this blue is okay. It's the water and a lot is masked out, I think, because this is zero connections.
Did you use what dates did you use? The same dates as in the
actually no, because here he used the descending mode, and this is my ascending results, and now I'm processing the descending, but I think the descending is a bit better. I just got the interferogram. So yeah, this is the interferogram from the descending mode. So the same as in the nice figure. And now I was just performing the unwrapping.
So this looks better.
Yeah, seems like a bit better, but still kind of, I see a lot of noise around.
So this is the descending, you say, and
yeah, this is I think the same images he had used, because it's not written which dates he had used, but it's descending mode. So this is the first image before and the first after the earthquake.
So I ran TopSap using for the same pair that Simone showed and I get a very similar result. I didn't
Like
use I didn't use the
Simone?
notebook. Yeah, I didn't use
Okay.
the notebook. I just ran it in on the command line, but you should be able to reproduce that.
Okay, by doing nothing special, or
Right.
there were some magic in your code.
No, really not.
Okay. Okay, then I will try. And I don't remember the masking of the water at which stage was happening.
It doesn't, but you can use the zero connected component as a
Right.
mask.
Okay, this is just for visualization, right?
Right.
Okay, okay, good. Okay, then I will check now this new.
Yeah, I was just looking for the dates that you may have used. I'm just checking what the interferograms look like, the ascending ones.
Okay,
Maybe that the
yeah, the dates are right.
you
Yeah,
should
this is
still get
3 and
coherence of-
15
Okay.
of
Yeah.
August, and the other was 5th and 17th of August.
Right. That's the first post-event image for both tracks. So that's
Yeah.
the last pre-event image.
Mhm.
So it should work. You're using
Okay.
XLTM.
So this is the one, but that's the, let's say that's the descending one, right?
This one is the descending one, yes.
Right. And for the ascending one, what were the dates there?
5th and 17th of August.
Yeah, so that one is not that great of an interferogram.
Okay.
There is
So that-
coherence, but it doesn't look as pretty as the other one.
So the descending is better.
The
Should be
descending is better. The ascending seems to have a lot of atmospheric distortions.
Okay.
If you want, I can show you real quick.
Yeah. I have to. Yes.
See here. So this is the one that you tried to process, I think.
Mhm.
This is the 5th of August to the 17th of August.
Yeah.
And yeah, and so the ascending one, not sure which one that is. Earlier. This is
Yeah,
the one
this-
that you tried to
this
process.
one.
I think.
Yeah. This looks nice.
Yeah. Yeah, so it looks like the other one looks better,
Mm,
even before filtering.
okay. So, okay, I will try, continue trying. Okay, thank you.
Other questions? We have another 10 minutes.
I've been in the chat box, but I guess I can ask it. I was having trouble with the TOPS app finding the DEM. And I wasn't sure if I needed to, do you need to bring in a DEM separately, or does it find it automatically based on your bounding box and download it? And if so, I couldn't get it to work if it does that automatically.
It does it automatically based on the orbits and the timing of the image.
Okay. So I'm probably having a different issue that I need to figure out with the bounding box. It's a
We'll
pretty
figure-
small bounding box. That might
You
be
will
the
figure it out based on the bounding box which you have specified. If you're specifying a subswat and the bounding box is conflicting with the subswat as well, then there would be nothing to be extracted. Both of them need to be
Oh, I just did all three because I wasn't sure which subswath it would be in.
okay. Then yeah, then I would double check if are you sure that that long lat is included within the track?
I could double check, but I did it based on the vertex, what it was giving me back as the coordinates when I downloaded the data. So I
Okay.
copied it directly from the WKT. I mean, I reordered it, but I copied the numbers directly.
Okay, so one thing to do could be the step before when it's doing the initialization, it will tell you how many bursts it has extracted. So perhaps double check if that is not 0. So sometimes what you see with ICE is that even when it extracts 0 bursts, it will continue running and then it will run into a DM error down the line. So there might have been something earlier on that might have indicated a potential issue with the bounding box. If that is not the case and it extracted a burst, then it should normally fetch the DM fine. So we could work from that.
Okay, just make sure that it actually got some bursts when I told it to.
Yeah.
Okay. All right, well, that's a good start. I can start troubleshooting from there, I guess.
I mean, you could also try commenting out your bounding box and seeing if it downloads the dem at all. You don't have to run it past that into topo, because then it will try and
If I do that, would it just do
everything.
the whole,
yeah,
like all 3 subswaths then?
yes,
Oh,
which
okay.
will take a long time. But
Oh, it might be
at
worth
least
it
know
though.
that-
Okay, yeah, that's a good thought.
Hello, everyone. This is Yang. I have a question for David and Sim. So I have some problem running the area extract. Can I share my screen now?
Yes, please.
Okay. So yeah, can you see this?
Yes.
So the only thing, so everything worked fine, but the only thing I got problem is this one, the for the unwrapped phase. So when I extract that, you can see there's nothing shown in this plot.
That date, one of the interferograms you downloaded?
I'm pretty sure I have this. That's the only date.
I don't see the
Just
product.
for that particular 502.408, yeah, it's it just has a sanity check. You saw that there's a .png. Could you open that up in another tab from there just to see if it's not?
Yeah, there's nothing.
That's also empty.
So I suspect it has to do something with the water mask, Sim, that something went wrong. So if you, it might have masked everything here in this scenario.
And I also checked the .nc file. I opened that and checked the data. There's a nice interferogram there. So I think the extract didn't get this, didn't actually extract the successfully the wrapped phase, the unwrapped phase.
I think it's what David said. It's not necessarily it didn't extract it per se. It's that the water mask is probably masking everything out. So that's the water mask there. So that's kind of, that looks fine, David.
Yeah, everything else was reasonable, but only this one.
And how many? It's only one product, so it's not like it's doing some intersection and there's a small.
No,
overlap.
just one, because I just run all the cells from the top and everything else was fine. So you can see there's only this interferogram is asked. Yeah.
Yeah, could you try to run the plotting again of the water mask and execute the next cell again?
Okay.
Yeah. So now it's blank. So I think something goes wrong, that the water mask was updated to be just masking out everything. So I don't know where the water mask gets made in this case, somewhere before perhaps.
Right above there.
Loading a mask, this one?
Yeah.
Oh,
And that does take a little while. Just
Yeah.
Oh, okay.
hold on. Like takes like a couple minutes, 5 minutes or so, I think, up to.
Okay.
Yeah, so the water mask is fetching it from a certain server from, I think, either USGS from the national land use map, as well as the well-known safe trials similar to what GMT uses.
Okay.
There's two options to go ahead and do that.
Mask. Is there any PNG?
No, I mean,
No, not for this one. Okay.
No.
While this is processing, do we have anything else? There's a question. Mahmoud David, thanks. Okay, it's already answered.
There is a question on the slide. I think it's good. I think we could answer here. Could you hear me?
Yes.
Okay. So there's a question from Kang is asking the magnitude of the misregistration in the StreetMap app. There's two sentences. One is we said that the current available DEM and the orbits are accurately enough will give us a pretty accurate, which is actually a 1% of a pixel size accuracy for geometry co-registration, and that is true. And the misregistration we later on estimated has, I think these two units are either in meters or in pixels. Regardless of that, these numbers are much larger than the 1% pixel. And that is also true, that is because the misregistration we estimated through the AMCore amplitude cross correlation in StreetMap app is the contribution is actually mainly from atmospheric delay and more specifically for ionosphere, for L-band especially, which is huge, and we are actually working on that to provide that directly as an external data set. And that is also similar to what ISA is currently doing by providing this extended timing annotation data set called ETAD, presented in the Fringe this year, and they are trying to roll out that data set as a routine next to the SLCs in the next 1 or 2 years. So yeah, so both two numbers are reasonable and are expected from our understanding.
I have a question.
Yes, please.
When you turn on the property for doing the rubber sheeting step in the configuration file, do you need to modify anything else? Because I'm getting this error that is saying something about a class that's missing.
You might need to rerun the registration. Well, rerun the processing from a step before you do registration. Otherwise, it's going to expect the results to be there and they're not going to be.
Okay, so I need to go back to the misregistration step. Is that it?
Course registration, maybe. I don't know. This is where someone who's more of a developer might have the exact answer.
Okay, so I'll try going back further than I did to be able to do this, because I did go back like one step, but maybe I didn't go far enough. So thank you.
Okay, so I think this watermask is same as before, and everything was masked out in the unwrapped phase. So that's weird.
I think it gets overwritten, Sim. We should look into this.
Yeah, not haven't seen this one in a while, but especially the one product. But yeah, I'll have to investigate this.
Okay. Yeah, we can talk after this in on Slack. Yeah. All right.
Okay, it's I think about time for a 10-minute break, and then we move into a MintPy lecture by Yunchun, if that's correct. Alrighty, sounds like it worked.
Yeah,
Excellent.
thank you. It's just the bounding box issue, apparently. Thanks.
Okay, everybody grab coffee or whatever your favorite drink is, and we see each other in 10 minutes for a deep dive into MintPy.
take it away
Yes.
with MintPy.
Okay. Let me just share my screen.
Maybe some zooming in. That's great.
Okay. So shall we start? Okay. Great. So this is day 5 of our 5 days course on the InSAR training. And today we will walk through the InSAR time series analysis using MintPy, which is an open source Python package available on GitHub. So let's go to the OpenSAR lab. If you have previously, we updated the notebook a little bit last night. So if you previously has opened it or changed it, you should go to the 5.1 folder, delete this notebook, and then restart your server to update to the latest version. Here I have already updated, so just open it up. So you should also, it is set to the Unicode kernel by default, but you just check to make sure that it is the right kernel. So MintPy is called Miami InSAR time series software in Python. Is a package primarily developed by me and Harish, while we are in the University of Miami, and nowadays it has been contributed by a lot of users all around the world. The code will start from a stack of unwrapped interferograms in either geo or radar coordinate, and then estimate the time series. So MintPy is primarily consistent with the stack of interferograms generated with ISCE, but it also supports soft interferograms processed with other software such as Gamma, GMT-SAR, Snap, which is the one for ISA for Sentinel-1 mostly, and Webpack, which is a latency code. And MintPy is available on GitHub, open source, and you can find the link here. The software has its own paper, which is available. And if you are interested on the algorithm, the math, and then the detailed explanation on the workflow, you can check this paper. And another nice thing on this paper is that the data and the figures and the code to generate the figures are also available in here. And if you click it, and then there you will see all the data and figures, and you are supposed to be easily regenerate all the figures you see on the papers yourself. So in the MintPy, there is a one main application similar as ISCE has. We have seen the strip map stack, top stack. In MintPy, there's also one main application called Small Baseline app, and you can see from the names is implement the small baseline approach, or similar to SBAS approach as presented by Bernardino et al. At 2002, but of course it's a modern version, so it has big data friendly features. It has more careful handling of various aspects, which we will go through today also. So before we go any further, let's go to the first step of initial setup. Let's just run this one. And then to warm up the environment, this will basically import all the relevant modules and define the work directory, which will work at this directory. And then also today we will use the stack of infograms from ARIA, pre-processed by ARIA tools already. And I have already uploaded this data set to the AWS thanks to the ASF team. And let's just run this cell also to start downloading, since it will take a few times, some time. The downloading itself is actually pretty fast. You should see at least over 100 megabytes per second of download speed. After that, we will just uncompress the tar file. And later on, if you, later on, I also uploaded the exact same data set to Zenodo, which is another website to store your data. And it's also open access available. So if you have, if later on, if you don't have access to AWS anymore, you could change this to Zenodo, and this whole downloading will still work. Okay, since it's downloading, let's just go through what it does. The small baseline app is a workflow implemented the SPAS algorithms, and it mainly has two main blocks. One block is handling all the interferograms, correcting the RP errors in the interferograms, and inverting the interferogram for time series. And after that, in the time series domain, which then it will start to separate or correct all the noise from different sources, from atmosphere, from DM errors, and then separate that from the time series to get your clean displacement time series. And the whole workflow is illustrated here in this figure. So all the blue ovals are the operations done in the interferogram domain. All the green ones are the operations done in the time series domain. And we will start with a stack of unwrapped interferograms. When we mean stack, we mean that we have a lot of interferograms. They are consistent in space, which means that they should have the exact spatial coverage with the exact pixel size and the exact number of rows and columns, which is provided as it is from the stack processor, and which is also exactly the output of the ARIA tools if you run that, and that is what we run. So we start with a stack of interferograms, which is also what we call a network of interferograms, because it's a small baseline network. So sometimes if there's low coherent interferograms, because there's a lot, we generate that in an automatic fashion used these days. So there will be low coherent interferograms sometimes, and you can apply a network modification step to drop some of the low quality interferograms. And the next step is to select or set the reference plot point in space. We recall that InSAR is a double reference measure. It's a relative both in space and time. So in here, we want to select a common reference point throughout all interferograms so that the measurement among them are consistent with each other. You can also correct the RP errors if it is asked for. Then it will go through a network inversion step to invert the stack of interferograms to a time series. Then we will correct the tropospheric delays from various methods. And we can also remove ramps from the time series for each epoch, which sometimes, a lot of times, could be due to troposphere or atmosphere, or sometimes less extent orbital errors. And we will also correct for DM errors, and then give us a displacement time series. And then we can go for that to the velocity. So these are basically the main steps, and all these steps has options, and all these options are set in a configuration file here. This is the default configuration file. If you click here, this will bring you to the GitHub link. This configuration, it has options grouped by each step, and with a default value set as auto, and the later on you will explain for every option what auto means and the explanation of each steps. Okay, so now let's see if, okay, for me, I'm still running here also. So how does the application works? In here, we can just click this cell. It will bring up the help of these scripts. So this script is what you can call this script in one single command line. And you can also call that in a step-by-step processing, similar to what we have seen for StreetMap app and the TOPS app. And we can see here, there are these steps listed here. This is corresponding to the plot we just seen above here. It's the same thing. And you will start with loading the data. Then you start to modify the network, set the reference point in space. And then with a quick overview, this quick overview is just trying to do two things. One, stacking. Using the very traditional stacking method, we have a stack of interferograms. For each interferogram, we divided the measurement, we divided the phase by its temporal baseline. This will give us a rate measure, and then we just average the rate estimate for all the interferograms, which somehow give us a very simple, a quick overview of how your velocity might look like for this stack. Then it will correct for arm errors, invert the interferograms into time series, correcting for LOD. LOD is called local. So all these steps is also with detailed explanation in here in the bottom with words. Let's go back. Let's go here also. So LOD is called the local oscillator drift. Is a thing specific for MVSAT. There's a drift problem on the radar sensor there. So we implemented experimental model developed by other people to correct for it. And this will be turned on automatically if it is a MVSAT data set, and turned off automatically for all the other sensors. So you don't need to worry about it. You can also correct for SET, stands for solid earth tide, which is implemented recently. The solid earth tide is a gravity pull between the sun and the moon and the earth, which will also introduce a long wavelength deformation into the InSAR measurement. We will also correct for the troposphere, and it supports in MintPy supports several methods, which we will go through details later on also. And then deramping, remove the ramps, and then correct topography to estimate and remove the DM errors. Later on with the residual RMS, this is a very simple noise evaluation steps to try to guide us laterwards on how noisy each acquisition is, so that we can get a more slightly improved estimate of DM errors and velocities. After all this, then we'll go through the output, which you can geocode them if it's radar coded. For our stack, in this today, it's geocoded already. So this step will be skipped. It will generate Google Earth KMZ files for you to easily check on Google Earth. It will generate a HDF EOS file, which is a specific H5 file defined by NASA. And then we inherited from UNAVCO also. So basically, this is one file which we hope to serve as a generate exchange format. It should include all the information needed for an InSAR time series, so that you can save all the information in one H5 file and then share it with other people. So now, I believe most of you should also already complete these steps, and then these steps will give us the staged data downloading and unzipping. And now we can go to the next steps. So we see all the processing steps, and for all the steps, it will be configured, it will be set it up through two configurations files. One is a default configuration. It's called small baseline app.cfg. This contains all the configuration parameters as you already seen in the GitHub page just previously. They are all grouped. They are grouped by each different steps with default values, and then you can check what the default values in another file called this name. If you click it, it will bring you to the GitHub page, and you will see all the default values. And optionally, but we recommend it that you also use a custom configuration file. In this dataset, we use a configuration file named this one. So this configuration is a manual configuration. It's optional, recommended, and the name is arbitrary, so you can give whatever names you want. And this configuration file will have a higher priority than the default configuration. So if you feed this configuration file to the small baseline app, it will read it and then update the default ones based on these custom ones accordingly. So this is actually what I usually use. I usually use this one for myself and then keep this one for the code to read all the things they need. So in here, for this configuration file, for this dataset, it looks like this. In here, the top part is where we tell the program where all the stack of interferograms is. So in here, let's just first run this cell. It will says it will write all this file, write this content into a TXT file here. And then let's just run the bottom one also to just load the data set. So in here, if we run this one, it will start to load all the array products into MintPy. And you can see from the output, there's a few useful information here. It will tell us where the current directory is and which step is running. Currently, it's running the load data similar to StreetMap app, and what the remaining steps are here. So previously, what I mean is literally this. You can see the program in the top in here. We feed the custom template file to the program. So in here, you see that the program is read this custom template file and then update the default template file based on that. So it changed the auto to area. It changes this to that. It changed a few other steps. And then the program start to load all the data into HFile files. And we can see that the process is here. So everybody's following on? Just check that. Okay, great. Okay, so let's go up a little bit to explain what is happening. If we check this template file, we can see that on top of them are the input files. These three are the first of the unwrapped phase. The second one, you can see it guessed from the name mostly. The second one is the spatial coherence for each interferogram. And the third one is the connected component. We will see how that looks like also later on. The second part is the the second part is the geometry dataset. We will feed it with a DEM. We will feed the instance angle of the line of sight vector, loss vector. We can also feed the azimuth angle of the loss vector and the water mask also. So the top part are the inputs. The bottom part are the processing configurations. In here, there's a lot of configurations. So in the first one, we will just turn all of them off and then just do a simple time series inversion. But we still need to manually specify a reference point. So you will also, when you experience MintPy more, will realize that most of the steps are pretty automatic, except there's one step, which is usually manual and which is the reference point. So reference point is not automatic because I think it's difficult and I didn't find a way to make it good and automatic. So I always recommend users to manually select a reference point based on your knowledge on your study area. So in this case, I already know my starting area pretty well, and this is the reference point I'm choosing. And I chose that based on a few criteria, which you will also find in the template files with the guidelines. So to me, a good reference point is that it first needs to be coherent, so it does not affect by the decorrelation noise. You can see that from the average spatial coherence, which will be generated later on. So that's first, it has to be coherent. Second, it should be close to your signal of interest, because when it's closer, then the spatially correlated noise is also smaller. But you cannot use, but sometimes, as for example, as a volcano, it cannot be too close, right? You want to still stay in a relatively non-deforming areas. But of course, if it's tectonics, you don't have non-deforming areas. So for example, for volcanoes, it should be close. What I usually choose for volcano is, if I know one volcano is active, I will choose a nearby volcano that is not active, but in a similar elevation, so that so it's both close in horizontal space and also vertically, so you will have less impact on the tropospheric delay. And this is experimented a lot by Estelle and Aneri when they did a lot of volcano surveys. So in here, let's just ask one question. Our first question is here. We talk about this a lot. What are the inputs of MintPy? So when we say stack of interferograms, are the multiple pairs of interferograms produced by TOPS app by default without manual settings stack? Let's see if you could answer that in chat in the chat. Okay. Okay, so a lot of people say stacks. Okay, great. And then let's follow by this. In here is the figure on the right, a stack of interferograms. This is basically a very simplified illustration of what the interferograms were produced if you just repeat the TOPS app or StreamHub app for a lot of pairs of interferograms. And we can see that usually if you don't specify the bounding box, it will have a little bit different, slightly different spatial coverage. And this part is, if it's like this, then MintPy cannot really handle that. MintPy assumes always that all the interferograms are exactly consistent in space. So if you generate interferograms like this, the most simple way is to geocode them into the exact bounding box, as already asked yesterday by a few people. Okay. Another thing I want to also note here that in the top on the processor, we said here, this is the processor generated by area. So that's why we use these names, because this is specific to each processors. And MintPy also support interferograms from other processors' ISCE with all its processors, area, which we're using. It also recently supported the HiP3 from area, which is contributed by Forrest Williams, which is also in here. And thank you very much, plus the SF teams. And it supports GMT-SAR also, and the SNAP, Gamma, and Wirepack. Sorry, so let me hear there's a couple of questions in here. Let's see if. So to Jesse's question, he is asking, can you turn these steps on and off, or they're all required? All the input files are required, and all the other non-input files, processing configuration files, are not required and optional. And all of them are, if they are required, they will be noted in the GitHub configuration files. For example, you can see here, if it's optional, you will say optional but recommended. If it's not optional, then it's required. And after the input file here, since step 2, all of them will have default values. And since it has default values, so of course you can just don't put anything and it will grab the default values for you. Okay, I see Harry's already answered that. Great. Great. I see Garrett is also answering. Okay. So let's move on. In here, you see the loading process is already done. And we can see after loading, it generates, okay, it's finished. So we can see also after this process, it will generate 2 files, all of them in the inputs directory, subdirectory. And if we just run that, you will see that it generated, you can see this date, it's just generated right now. It will generate an interferogram stack file, which is all the interferograms. It will generate a geometry file to include all the geometries, and it copies over the 2 template files also for backup purpose. This file is the tropospheric delay, which I pre-generated and uploaded into the tar file. So the interferogram file, it has this following 6 dataset. It has a dataset called date. It's a 2D dataset in the size of this, where M is the number of interferograms, L is the number of lines, and W is the number of columns. So date is it saves the date of between the two dates of the interferograms, the reference and the secondary date in the stream format as this. Bperp is a perpendicular baseline or 1 value for each interferogram. Coherence are the spatial coherence of each interferograms, kinetic components, the erupted phase. And the last is a flag dataset called drop ifgram. This is the 1D dataset in Boolean, so it will just indicate later on whether we want to use this interferogram for inversion or not. And the geometry dataset includes all the geometries. So so MintPy is using the H5 files, and then you want to know, if you want to know how the H5 looks like or the information, you can just run the import.py, which is a script very useful in MintPy. It actually supports generic any H5 files, not just the files generated by MintPy. If you just run the import.py, you will see it looks like it will report the file names, a file type. This is a geometry file. This geometry file is in geo coordinate, and then with all the attributes, it's included in the root level, the name of the attributes and the values. And if you scroll down, it actually includes all the attributes it's found, plus the MintPy configurations for your reference too. And you can see in the bottom that it has this few data set, which we just specified in the template file with shape like this and a data type like this. Similarly, we can just run the same thing for the interferogram stack. It generates the same thing. It's in geo coordinate. It has all the almost the same attributes. And on the bottom, you will see these data sets with a 1D data set for perpendicular baseline, a 3D data set for coherence. In here, we can see that it includes almost close to 600 interferograms in a row and a column number of this. So, okay, now let's just, before we do the inversion, I think it's useful we just look at how the network or the stack of interferograms looks like. We can just run this cell and it will start to plot this network. And you can see that it's similarly plotted and previously in the Area Tools notebook too. So this is just a network of the interferograms in a plane of, okay, let's just wait for C. Okay, so you can see it generated a few plots. The first plot just shows the history of the particular baseline. The second plot is a coherence plot. Both the X and the Y axis are the image number. So each grid here shows one interferogram, and the color of the grid shows the average spatial coherence for that interferogram. And in here, of course, it's totally symmetrical, so that the top triangle and the bottom triangle are exactly the same. This one is not super useful, but let's focusing on the last one. The last one of the network. So you can see here, basically, we know that pretty familiar already. Each dot is one SAR image. Each line shows one pair of interferograms. And then the color of the line, as noted here, shows the average spatial coherence. And this file will also generate, this script will also generate a simple TXT file named this, and this will just save all the information that is just plotted here in a simple TXT file for your references. And also, before we do the inversion, let's just try to check the masks. These are used for quality measures to see the whole stack. With first one, we could just generate an average spatial coherence from all the coherence we have for each of the interferograms. And you can see that it looks like this. The blue, the very black ones are water or no data. And we can see that visually, just from this map, we can know that all these bright parts are pretty good. And the gray parts are more or less maybe not so good, and we need to pay attention. And also similar in here, in this within the coastal area of the San Francisco Bay, it has a pretty gray and low coherent also. And this brings us to another thing called in MintPy, there's another useful script called view.py. We can call them in notebook as this form. And if you call the same thing equivalent command in the terminal, it just looks like this. So you can see they're very similar. Similarly, we can also plot the water mask, which we specified generated from array tools. It similarly looks like this. And then last, we can also generate the mask for kinetic component. You remember, for every single interferograms, we have one kinetic component. So in this step, it actually just generate what they call the common kinetic component, which is the pixels that has non-zero values among all interferograms. So this part, this is basically at least a conservative mask to show that for those pixels, they have been identified by snafu, have valid RMP errors all the time. And you can see it look like this. That's why I say this map is conservative, because you can see it has much less bright areas. So the next step before we do the inversion is to specify the reference point. Let's just run it here. The reference point is, again, selecting one common spatial reference for the whole stack of interferograms so that they're consistent with each other. And in here, you can see it's very fast. This is because this step is actually did not touch the data itself. It actually just add these few metadata into the files without changing the data value itself. But this metadata will be considered when MintPy later on use it to do the referencing on the fly during the inversion. So you can see that still we can check the metadata here by using info.py. You can see that it adds these few metadata into the HFIL files. These two are what we specified in the template, and these two are the corresponding column and row numbers of it. So, okay, so now let's just do the immersion. So you can see MintPy is running. You can see that it actually split these big file into 3 patches. Is what MintPy implemented as this block by block processing to save the memory. So in here it split this file into 3 patches, and process each patch one by one. And on the top of this, printed message, there's usually some useful information also here. This is basically the printout of the configuration we added into the template. So you can see that the program is applying a least square estimation with an L2 norm. A least square, just scroll down. It's applying a least square estimation with L2 norm on the deformation velocity. We'll explain that what deformation velocity actually means later on. It will constrain a minimum redundancy check for each interferogram. We did not apply weight here, and we did not apply any masking here. And you can see that these are the number of interferograms we have. Out of this, there's around over 150 acquisitions. And you start to generating the time series files. Okay, it's processing all of them one by one, and it starts to, okay, finished. So this step is generating a couple of files. The main file is called the time series.h5. These are the time series that we want, and we can still run the info.py to see how this time series file looks like. We'll still show the basic information. It will also show some statistics of the date of this time series. And then again, shows the H5 files configurations. I didn't plot all of them here, and to show the dataset. So in the time series file, there are 3 datasets inside of it. One is a perpendicular baseline in here, 1D dataset, a date, 1D dataset, and a 3D dataset for the time series in the shape of this. So the first one is basically the number of dates we have. And also note that this time series file, since MintPy started at time series, it will also convert the unit from radians into meters. So and also revert the signs. We talked about the sign previously as consistent with ISCE2. If the unit is in radians, and we also assume that the later date is the secondary date, the earlier date of the reference date. And with this convention, then positive phase in radians means it's a range increase, then the surface is moving away from the satellite. But when in MintPy, when it converted into time series, it will change that into the unit of meters, and in meters, MintPy always assume that if it is a meter and the value is decreasing, then it means it's moving towards the satellite. Then in the case of vertical deformation, in MintPy in the time series, if it's a negative value, then it means it's substance. So that is more closer to a geophysical sense. So in here, let's just ask one question here. We did all the things to get the time series. Why we invert a network of small baseline interferograms to get a single reference time series? And why, instead of forming a single reference time series at the first place directly from the SRCs? Let's see that. What do you think in the chat? Why we want to invert a network of small baseline interferograms? Why don't we form a single referenced network of interferograms directly, which is literally already directly a time series? If someone want to speak up, they can also welcome to speak, unmute themselves.
Forrest provided an answer.
No, in this step, I don't have provided answers. I think it's a good discussion here to just speak up or type your answers in the chat. What do you think?
Yeah, so there's one response in the chat right now by Forrest Williams.
Okay. Yeah, for success is to maintain the high coherence in the interferograms. Yes. You remember yesterday in David's presentation, in the very beginning, there's a plot showing for a lot of interferograms. Right, great. Okay. Okay, great. Seems like you all got it. Right. So that's literally what the community has did for the last 20 years, especially in the 2000s, to minimize the influence, to minimize the decorrelation noise, because small baseline interferograms has higher coherence, thus less decorrelation noise, and that will keep the spatial coverage of the InSAR measurement high all the time when we get a very long time series. Okay, so now, great. Okay, so now we have the interference, then we can just do a simple linear estimation or linear regression to get a linear velocity here, just to see how it looks like. So these are the next step already finished. Now let's check how it looks like. So this step will generate a file called velocity.h5, and I can just plot them by running the command below. And it looks like this. So how far is everybody following on to get everybody successfully get this map? Okay, great. Okay, so I'd like to follow on Harash's tradition to stop here to discuss what we see from this map. This is currently just a simple velocity from the interferograms we have, and we didn't do any fancy corrections. We didn't do any uncertainty estimation. And what do you see from here? What are the features? For example, let's first check what are the tectonic features you see from this map.
Would it be helpful to point out the color, the sign convention for deformation?
Right, thank you, yes. Yes, that's always very helpful. So in InSAR here, we can see that the unit is in the centimeter per year, and the blue colors are negative. So it's for moving away from the satellite, while the orange and the red colors are positive, means it's moving towards the satellite. And in this data set, we are using the Sentinel-1 descending track number 42. So we know that the satellite is descending. That means if you can see my mouse, the cursor is moving from, it's moving downwards, right? It's moving downwards, and we know that Sentinel-1 is a right-looking radar. So it's moving downwards and it's looking towards this direction, from right to left. So, and this part is moving away from the satellite, and this one is moving, and the red ones are moving towards the satellite. So, great. So I see people see right lateral structurally. Right. Okay, great. Yes, that's one of the, that's definitely one of the main signals here. So any tectonic people or geologists who might want to speak up? Go ahead, Gary.
I think, okay, so one thing you can see is the motion of the whole plate boundary between the red in the west and the red in the east and the blue in the west. Everything in the west is moving with the Pacific plate, which is to the north, which is moving to the northwest from here, and everything on the right is basically more associated with the North American plate. So that transition from blue to red is basically the bending of the plate boundary zone caused by plate motion.
Great. And to add up to Garrick, is that we know that the Pacific plate is here, North American plate is here, and the plate boundary is the San Andreas fault, which is around here.
Well, I would say the whole thing is the plate boundaries.
The whole thing, right? Right. And from previous notes, it seems that the plate boundary motion here is around 40 millimeter per year. And we can see that in here from the blue to the red here, there's a slip rate of accumulation of around 15 millimeter per year. Why? Yeah, like 15, 20 centimeter per year, millimeter per year of slip rate. Yes, okay. Okay, said it right. Okay, so yeah, so it's actually it's a strike slip fault. So we have the strike slip fault system, and we're observing that in InSAR in line of sight with instance angle of around 30 to 40 degrees, and that will give us a projection of that 40 millimeter into line of sight, which is around 15 to 20 millimeter.
There's a good question by Alex that you should probably address one more time. He's saying, it's interesting that it's green in the middle, so there's no movement at all. So maybe you can address the reference point question
Right.
one more time. Yeah.
Right. So to that question, we know that InSAR is referenced. InSAR is a double reference measure. It can only measure relative motion both in space and time. So that's why in here we put a reference point here. So everything that is moving relative, all this map is showing the movement relative to this reference point, which is the black square here. So that's why all the things around here and on this side of the fault is green. Thank you, friends.
Yeah, and I just saw that Gareth already answered in the chat. It was faster.
So anyone can see how many faults we can see it here. Okay, Alex already said that. Great. So we know that the San Andreas fault is floating around from here to here. And then this part is Hayward fault. And this part is Calaveras fault. And this part is Concord fault, right?
Right. And there's to the southwest of the San Andreas is the San Gregorio fault, which you can't really see. And to the east of the Calaveras fault is the Greenville fault, which you also can't really see. But the point is that, yeah, people are saying, well, it doesn't seem that there seems to be off-fault deformation or whatever. Really, it's just that the zone is very, very big, and you have to sum all the motions of all the faults really to capture the full plate motion. So the San Andreas is the fault that's moving the fastest, and that's the one that we say is the plate boundary. But really, it's a zone that's 100 kilometers wide or so. And two of the faults are creeping, which is cool. And the Calaveras is too, but that's harder to see because it's got a more north-south orientation.
Okay, so okay, there's and besides the tectonic signal C, here there's also a hydrological signal. We see that around here. This is around San Jose, the Silicon Valley. This is the Santa Clara aquifer system. We actually see that this system this part actually has an interesting deformation. This pattern actually the color changed from this year to previous years. We'll see that more later on in the time series. Okay, so did anyone see anything unusual on this map that you are not expecting? Let's see if people can find it in the chat. In here, and north of, right. There's one here, right? There's looks like something is off around here. Yes, the south part is due to the substance, due to the groundwater. The top part, I don't know what the top part of red is actually. It's because of what?
Almost certainly groundwater. You could also see in the sort of the southwest bay, there's a really dark blue spot on the coast. That's Foster City. Yeah, which is subsiding. It's all built on mud, basically. The mud is slowly compacting, settling, and so that whole area is subsiding. You see similar subsidence in all around the edge of San Francisco Bay, including at San Francisco Airport and in parts of San Francisco itself. So there's this sort of darker blue features that you can maybe make out along the coast on both sides of the bay are probably mud settling and compaction, and buildings slowly sinking.
Okay, so I see Alexandra got it right. We hear there's an offset in here, and also seems like in here. And these are later on we'll see that this is due to another thing. What I would not say here to spoil. There's a Proston effects here, and we'll address that in our second session. So now let's just see one more thing that also we mentioned that in David's lecture yesterday. MintPy, like other InSAR processors, currently does not provide the uncertainty or report uncertainty routinely, and they still work on that. But we do provide one measure, which is the goodness of fit of the linear velocity to the time series, which it looks like this. It's saved in a velocity STD dataset. It's still again in the velocity the H5 files, and we can just plot them as here. Note that this velocity actually is this uncertainty is actually very small. It's definitely underestimating the noise we have, and the reference point is still here again. And we can see that a few features. One is that for pixels away from the reference point, we're getting slightly larger uncertainty, which is expected because there's a lot of tropospheric noise. Tropospheric residuals or tropospheric delays are spatially correlated. And we can also see here, there's some larger values on the Santa Clara aquifers, which is because we are estimating the goodness fit of the linear velocity. And if the deformation is nonlinear, then of course the uncertainty for this part will be high. So that's the major part of the first session today. And before we take off, I think let's just go to one more notebook. If you go to here, go to the visualization folder. Yes, we will talk about the reduced uncertainty later on in the session. Yes, also those track and look orientation could be plotted. We just did not do it. Somebody, if they want to, feel free to, definitely more than welcome to contribute. So let's click the tsview.ipy notebook. This is an interactive notebook, and in here you need to choose the UNAVCO kernel also. And in here, if we just first run the first cell to warm up, and then run the second cell, I think here you might need to change it, or you might not need to. I think I forgot to update this part. In this part, since currently we only have the time series .h5 file, we don't have the later on suffix. If we just run this file, it will just start to reading and plotting. And this is called tsviewer. Tsview, which is there's also an equivalent script called tsview.py in MintPy to plot the time series. This is a script originally written by Piyush in Giant, and we adapted for MintPy too. We just zoom out a little bit here. So we can see that this is, for example, if we just plot one thing, it will just show the time series on the bottom. It now by default just also plot the prediction of the linear velocity here also, just for a reference. This is a simple linear velocity here. And we can see that in Santa Clara Valley here, you can see the time series is relatively complicated. And that's why we see that the linear feed doesn't work well at all. And that's why we also previously see larger uncertainties here. And if we can plot other places also, you can see that if we choose a point nearby, it's very narrow. And if we choose a point further, actually get more sparse. This is also because of the specially correlated noise from troposphere. So yeah, so this is one useful script to play with your time series so you can get more familiar with the data set. There are a few other scripts also. Let's try one more, which is the plot transaction. If you open that, same thing, set the kernel. And run it. So what it does is just plot the profile. In here with the velocity here, you can plot the profile as this. You can clearly see the creep crossing the Hayward fault. You can also plot here and like that. So it's a useful tool to check your data set. So that's for now for the first session. See if you have questions we can answer before we take off for this one.
I have an odd request. Can you go back to the transect and do another one across the Hayward fault? And I'm just taking screenshots for advertisement. Okay, there you go. Thank you.
Okay. Okay, so that's it. If there's no more question, let's take a 10 minutes break and come back at 12:11, 12:10. Great. Okay, I think it's time to start. Okay, so this section we will go through the error analysis in a time series, trying to figure out what is signal and what is noise in the data. And in this part, I'm assuming everybody is back, right?
Just try to goad them into saying yes or no, so that we know if people are ready. Yay!
Right.
Thank you.
Great, thank you. So for us to understand what is signal and what is noise, we need to understand what is in the phase that we have. So this is by no means a generic or comprehensive representation, but of course I think this will help us to understand why MintPy is trying to do the way it does. So we know that we see a similar equations from a lot of presentations, and in MintPy we divided them into two types. With a phase we have, there is a deformation of interest that we would like to have. There is atmospheric delays, including ionosphere and troposphere. There's a geometry-related phase contributions from the DM errors or potentially orbital errors, and there are tidal effects, which are such as the solid Earth tide, ocean tidal loading, pole tides, etc. And there's the other type, whole different category, what we call a non-closure phase. And these are the phase contributions that does not fulfill the zero phase closure of a triplet of interferograms. What does that mean? So we have in the interferogram, we have three images, A, B, C. We can form an interferogram, AB, AC, and BC. And so theoretically, AB plus BC should equals to AC, and sometimes it doesn't. The part that make it doesn't is what we call the non-closure phase. And it actually includes the decorrelation noise, the potential phase arcing errors, and the processing inconsistencies due to filtering and multi-looking, which is very small. And the last part, the non-closure phase from sometimes the short temporal baseline interferograms. The last part, which is currently still an active area of research, there's a lot of great work done by DLR, by Francesco Dezam and Homo Ansari. And there's also new work done by Yujie Zheng, a postdoc at Caltech, my colleague, and with Haresh. I believe the paper are already under review. So we'll see more about that soon. And then I believe the plan is to implement that algorithm into MintPy also once it's ready. So why we do this? Because there's these two different types, so MintPy handle two of them separately. In the first step, we think in the first step, which is the inversion part, we put deformation, atmosphere, geometry, and tidal, all of them, their closure, they fulfill the closure measurement, they fulfill the closure criteria. So we put all of them together and then treat them as signals. While in this step, only the non-closure phase are noise. And then by this step, we'll try to minimize the impact of the non-closure phase, get to the interferogram, get to the time series domain, and then in the time series, we will start to separate the atmospheric delays, geometrical impacts, and tidals from the displacement. So we treat these two separately. And to treat this, that's why we also has two different subsections. In the first subsection on the quality of the inversion, and we know that the inversion depends on the closure phase, and this part of non-closure will impact the quality of the inversion. And for this inversion, we will there are several different measures or metrics that we could check to see how good or bad the inversion is. One is, of course, the average spatial coherence, which is a convenient measure to see the overall decorrelation noise, because we know with stronger decorrelation, we get larger phase variance and get lower spatial coherence. So this is one thing. We can see that basically from this, we know that the areas with bright colors should be more trustful. The second matrix is called temporal coherence with more details in this paper here. And it's calculated as these equations. Here, the delta phi is the interference matrix, is unwrapped phase. The phi hat is the estimated time series phase, while A is just a design matrix fulfilled with 0, -1, and 1. And by doing this, we calculate a temporal coherence, and this temporal coherence is literally measuring the closureness of the triplets. If the triplets is closed well, then the coherence and the temporal coherence will be high. If it's not closed well, then it will be low. This is normalized so that you will have a temporal coherence value varies from 0 to 1. With 1 we like, with 0 we don't like. And from the experience, if you have a dense network of interferograms, a threshold of 0.7 should be used from our experience. And for me personally, I always use a threshold 0.7 or higher if my network is not redundant enough, because of the question below. Let's see if people can answer that. This is how the temporal coherence looks like. So in the last session, we see that there's a weird pattern here, right? And we can see that also now clearly in the temporal coherence that there's a line here between this and this. And so that's one of the reasons that I usually like temporal coherence better. And we say that for a network of interference with only one interference without redundancies, then how the temporal coherence will look like. Anyone want to try to answer that? If you have in here, in this stack, we have around 150 images. We generated up to 600 interferograms, so we are pretty redundant. And what if we only, with, for example, 100 images, we only generated 99 interferograms? And how would the temporal coherence looks like in that scenario? So the equation is here. Right. So Carrick answered, great. Yeah. So literally based on this equation, if there's no redundancy, then this design matrix A will be exactly perfectly solved without any optimization. Then in that case, theta 5 and 5 are exactly equivalent with each other without any differences. And in that case, the temporal coherence will be perfectly 1 everywhere. And in that case, then it's basically useless. So here's to the other question. In most of the time, the temporal coherence will resemble the spatial pattern of the spatial coherence. As we see here, these two maps are pretty similar. Under what condition an area with very high average spatial coherence may show a very low temporal coherence? Let's see what people have in the chat, or if you want, speak up also freely. Atmospheric delays, atmospheric effects, high deformation rate, snow cover. In snow cover, if it is snow cover, we will get decorrelation. Then there will be low spatial coherence also, and low temporal coherence, I assume. High deformation rate, I think it's the same thing. Is if the deformation rate is super high, like exceed the limit of InSAR detection, then it will introduce low spatial coherence also. Atmospheric effects usually does not impact the spatial coherence very much. I would imagine that actually could lead to another reason. Okay, so topographic variation effects. Not really. Okay, so let's nonlinear deformation. Is something SWAS related? Okay, it's related with what? Here, what we want to see is we want to see the quality of the inversion, right? And the inversion quality depends on the non-closure phase. And what are the non-closure phase? We see here already, non-closure phase includes decorrelation, which were represented by spatial coherence, which includes potential RMP errors, and includes the non-closure phases, which is not universally accepted understanding yet. So if we, so what do you think? What do you think? Then the reason should be among this few, right? Which one among this few would cause the different appearance between temporal coherence and average spatial coherence? Right, great, yes. So that's the RP errors. RP errors will break the consistency between interferogram triplets. That's why I like it. So let's see how it breaks. In here, this is going to a little slightly deeper. Again, we have 3 interferograms, IJK, and then with IJK, we can form a triplet, and then there will be a triplet phase, what we call the closure phase, as C here. Then this C phase will be non-closed if there's RP errors. But we know that phase RP is operations that only adds the integer number of 2 pi into your phase. That's all RP, that's all phase RP does. So if there's an RP error, then that means you added the wrong integer number of 2 pi. So here, that's why we added this operation to extract only the integer part of the closure phase. And we can do that for one triplet, and we can then do that for all the triplets. So in here, by this equation is T int, is trying to calculate the number of triplets that are not closed, the number of triplets that has non-zero integer ambiguity. For, it's a long word. Okay, let me say it again. T int is the number of triplet that has non-zero integer ambiguity. If you have non-zero integer ambiguity, you have RP errors. And then, so this part is trying to count how many triplets has RP errors. And we can literally do this operation here. If you just run this cell, this is one of the 2 steps is done, one of the 2 operations done in the quick overview steps. And in these steps, it will literally run these equations and then generate a file called these names. I know it's long. I don't find a shorter name myself. Okay, she's done. And then again, this one is plotting that. So it looks like this. This is the part that we see a similar map from David's presentation yesterday also. So this map is literally showing pixel-wise T int value. Again, T int is the number of triplets that has non-zero integer ambiguity. Means that, so what it means? It basically means that when the T int is 0, all the triplets are closed. All the triplets are closed in the integer sense. So all the so all the pixels, if there's 0 T int, it's pretty safe to say that they don't have RMP errors. And all the pixels, for example, here, you can see that they're in a different value, but often they're pretty homogeneous. It seems like they're sharing one common T int value, which means that they have RMP errors, but this RMP errors somehow is consistent, and maybe we could correct it and use it. And for this part, you can see they are pretty random. RMP errors, and this part is represent very random and difficult RMP errors that is pretty hard to correct. And we can see that same thing in the histogram here. So we can see that in the histogram, this is 0, and also note that this is log scale. So these spikes are significantly higher than all these parts. So we can see that usually basically this from this map, you can see that there's a few spikes here. They are corresponding to, I think, around 30, 40 triplets with non-zero energy ambiguity. That means there's quite some of them has RMP errors. In here, also you see another spike. It's not 0, but it's pretty small. There also has a very few RMP errors here. So this is what we call is a very good parameter to detect or identify RMP errors in your data set. So that's why, so here we can see that this clear jump is consistent with the offset we see in the previous velocity. And this jump is also consistent with the temporal coherence. We see the differences here. So from this, we know basically that there's RMP errors here. So what do we do? There are basically two ways. We can either correct the RMP errors, or we can just drop them. We know it's bad. If we cannot correct it, we can just remove it. So first way, obviously, is just to identify those pairs of interferograms that has RMP errors, and then remove them using network modification, basically by dropping a few interferograms. There is a lot of options in MintPy to do that. Before we go into details, let's just check this final equation. This one of the questions here. So we now know RMP errors, right? We will go to that on the automatic way to correct it. So the question is, after time series inversion, which matrix better represents the quality of the inversion? A, average spatial coherence, B, temporal coherence, C, the common mask in the kinetic component, and D, the water mask. Let's see your answer on the chat. Great. Then everyone is on board. That's awesome. Great. I love temporal coherence. It's one of my favorite things in InSAR. And okay, so we now know that we can check phase RMP errors in temporal coherence. And so we now, then we got the RMP errors. So how we do with that? One way is to do network modification. Another way is to do RMP error correction. So let's see first, we now know from that indirectly, we know there's RMP errors. Then now let's just check what RMP errors looks like in reality. In here, with this command, we are plotting the unwrapped phase for this interferogram stack. We actually plotted all the unwrapped phase with a range of -10 to 10. This is basically a good range, a good value range to show the RMP errors, because we know RMP errors are integer numbers of 2 pi, right? So that's basically -6 to 6. So we want to, I always just try to plot it in a value in a range like this, so you can see a clear jump into RMP errors, because sometimes you will have, sometimes by default, you will just show the range of the whole data set. It can be very large, from -30 to 50, then you don't really see the clear jump very well. So that's for me to check manually RMP errors. This is the data range I usually set. And again, it's using the view.py command. So all the files, if it is txt, if it's not txt, all the files in MintPy can be plotted with this one command. You should get very familiar with it, and you will love it. This is the favorite thing I love about Python and MintPy. Okay, it's a big data set, so it will take us a while to plot everything. So the Queen's question is it likely that the big errors like that are caused by some physical process, or is it just an error in the processing? RP error itself is from phase unwrapping, so it's a processing error. But this processing error sometimes can be due to physical processes. For example, for example, if there's a stream topography like Himalaya, or in some Baja California, there's some some big mountains too. In those regions, if there's decorrelation between in the top of the mountains, then it's really usually sometimes hard to unwrap across those mountains. And if there's water body separating your areas, you will get difficult unwrapping as well. And in this case, we will see that it's actually due to a third reason, which is our case. You can see this is how all the phase. You can see that it's a lot. We have around this much interference. And if we go back to the top of it, they are numbered. And we can see that just from a visual check, we can see that number 25, number 34, number 46, 61, 57, all of these has a very clear big jump. And this jump is the RP errors. And we can one way is to identify all these pair of interference and then exclude them. So this is what we did before. These are a part of the interference, the number that has RP errors. So we can actually literally set them here with this option, and then MintPy will just exclude them in the network inversion. So this is one way. Another way, which is usually what I like first as the first option, is to correct it. And MintPy provide two methods to correct for that. One way is bridging, which is a historic method. So we see that there's errors, and historically, we just in the community we just literally form a constraint. We know that, for example, in here between these two, we know there's nothing special, so they should be smooth in the face. So what we did is just force the smoothing transition across in the boundary, and MintPy is basically optimize that by using the kinetic component and force that smoothing. Of course, again, by adding only the integer number of 2π is still an unwrapping stuff. Another option is to do the phase closure in time domain. If you think of bridging is in a space domain by applying the smooth, by applying the constraint, then phase closure is in the time domain by forcing the consistency between the interference triplets, which is basically another equation. The equation is in the paper, so if you are interested, you can take a look at it there. There's a few options in this data set. We just try to use a bridge. So let's here just run this cell. It will write the option into the template file and then run this step to correct the unwrapping errors. So you can see what it does is trying to correct interference by interference as the date marked here, and is reading the unwrapped phase and then write a new data set with a suffix called bridge to it. And then MintPy, the script, will identify this data set then automatically, and it will be used later on for the inversion also. If you have a lot of pairs, it might be slightly slower, but it's still we really imagine it takes only like a little bit less than 3 minutes, so it's pretty fine. Since we're here, let me just show you one figure. I think it's useful to understand what it literally does. So can you see this PDF? Okay, great.
Yep.
Okay, so these are the process of the bridging. For example, these are the input interferograms. I plotted as wrapped, but it's unwrapped. This is the phase we have. On the D is the kinetic component generated by RP algorithms like Snafu. And we can see that, so the middle here is water. This is multiple islands. And we can see that the code is doing is grabbing the kinetic component, form somehow a minimum spanning tree network by connecting all those components with these white lines. I call it as bridging, to bridge them together. So what it does is basically just between the two endpoints of this bridge, it calculates the phase difference and then add an integer name of 2 pi to make sure that the phase between these two bridge points are within the range of minus pi to pi. So, so this is literally what it does. It does repeat the same thing for every interferogram. And the one in the middle is the residual phase. So this is the simulation, so where I know the truth. So B is the unwrapping result minus the truth. So basically, this represents the unwrapping errors. And before the correction, the unwrapping errors looks like this. After the bridging correction, the unwrapping errors look like this. So we can see that by this method, it could handle the big kinetic component pretty well. But we can still see that the small islands here and here is pretty hard to do because of the image processing techniques. So this method will basically take care of the big guy, but leave the small people go. And so now it's finished. And let's see how it looks like. On the top, we see that on the top in here, we just identified that a few of the interferograms has RP errors, right? Here, I just choose this one as an example, number 57. And let's just see for number 57, how it looks like. Again, I'm using Inforted PY. A good thing is Inforted PY with this, I can check the correspondence date of this interferogram. So it was numbers 57. By just doing something like this, I know that it's this date. And then here, I just plot this date. So this is how it looks like. These are, again, the same thing above. The interferogram with this date. This is before the bridging, and this is after the bridging. So you can see that there's a clear RP error here, and that the big part is corrected. And we can still see that the small part, which is very decorrelated, is not, let me show plot here, is not selected by kinetic component, so we cannot correct them. What it does is basically using kinetic component as the base to adjust the value marked by it. So that's why we need the kinetic component. And if you're using later on, if you're not using ICE or ARIA products, and for example, gamma, that does not provide kinetic components, and the MintPy then cannot apply this method to it. So basically, this is one example, and the code does it for all the interferograms. After that, we can just rerun the network inversion to see how the time series looks like. And we just run this step. Is everyone following on with running? Right. Again, it is still doing the same thing, patch by patch, and yeah. So what we're trying to do here is we corrected the RP errors in the interferograms. Then we rerun the inversion to check the new time series. We want to also, of course, check the quality measure of the inversion too, which is basically here, the temporal coherence. Oops. Oh yeah, so to your question, the RP error in this case, we can see that we know that this is a descending data. So the flight direction is around this, and then the line of sight direction is around this, which is basically perpendicular to this boundary. And we know that from yesterday's presentation, the area is doing the frame by frame processing. And after that, if we have data set across in different frames, we do a phase stitching. So this is a stitching error. When we this is a stitching error when we're doing large scale, or in this case, automatic processing. And it's pretty common in the ARIA tools, in the ARIA products, and so you should definitely always pay attention to that when you use it to make sure that you're not affected by it in your result. Okay, this is done. Now let's just check the temporal coherence. It looks like this. You can see the jump is gone. Okay, so we can see the jump here is gone, and we can see that on this island here, this is San Francisco. On this part is masked out. This is Golden Bridge, and there's a few islands here. You can see these few islands has low temporal coherence. And that means it could also possibly has RP errors, right? So the question is, if someone is interested on the time series at one of these islands around here, where would you put the reference pixels at? Great, yes, exactly, on the island. And because again, InSAR is relative, the RP error is also relative. So if there's RP errors between the island and this one, and your signal of interest is on the reference, then you don't have RP errors here, but you have RP there. We always cite together with reference points. Okay, so that's basically it on this first part, and there are a few more things that you can check, that you can try on the inversion part. We call that the modern version of SBAS because there's a few things. One is the weight inversion. We implement quite a few weighting strategies from various papers. All the papers are here in the template files if you're interested to check the details. What we have been using is a uniform weighting or no weighting at all. So if you want, you could also try to rerun the inversion with a data-dependent weighting. You can weight that based on your coherence, which you have. You can use the feature information matrix or the inverse of the covariance. Both the top two are also parameters derived from the spatial coherence. So what it does is literally for high coherent pixels gives higher weight, and for low coherent pixels give lower weight. And then since we have the temporal coherence, so MintPy by default use the temporal coherence as a quality measure and then generate a mask from it. Or what it does is using a threshold. As we said before, I'm usually using a threshold with a default value of 0.7. You could also apply masking into your data set if you think you have RP errors or bad qualities from your interference. You can mask them based on your spatial coherence or kinetic components. This part is for offset, it's not relevant for our stuff, for our case here. MintPy supports two different invert optimization criteria. What do I mean by that is the details is actually from Brandina's paper. You can minimize the least square inversion, can either minimizing the residual or the closeness of the triplets by minimizing the phase difference, or you can minimizing the derivative of the phase, which is the phase velocity. And by using the phase velocity, we could get it's better suited to constrain the multiple subsets of networks. It's a term from old days. That's why it's called SBAS. SBAS, its full name is small baseline subsets. And in MintPy, we didn't call them small S-bars because we like and we recommend always within small baseline without subsets. If you have subsets in mathematics, it's easy to prove that you will have bias, which we always don't want. If you have subsets, you don't have bias. And if you don't have subsets, that means the whole network is fully connected. Either both matrix A or B are fully ranked and non-biased. So the matrix B or the optimization based on phase velocity is a good thing, especially useful for old days when with multiple subsets, but it's still useful for now that doesn't hurt at all. So we use it still by default. There's L1 known and L2 known too, but L1 known is not tested at all, tested it intensively at all. So we currently just disabled it so that people don't get confused. Okay, so this is the part on the inversion. Now we know the quality of our inversion, which is not good here. We can go to the next step to check to reduce the noise level in the time series. In this part, we start to treat all the things, in this case, all the things that is not deformation noise. This includes atmospheric delays, DM errors, tidal effects, and then so MintPy has options to treat them one by one. First one is the local oscillator drift for MVZ specifically. Another part is the solid earth tide. Solid earth tide is the tidal in a solid earth due to the gravity pull between the earth, sun, and the moon. It's actually especially useful if you have a large area processing, like for example, crossing the whole Tibet or crossing the whole US continental, then the impact will be significant and not negligible. MintPy has implemented using another package called PySolid, which implements another convention, which is pretty well accepted. So what you do only is to set this auto, which is no, to yes. Then it will do that for you. Another part is troposphere, which we know that it's one of the dominant noise in the time series. And there are several options. One is the empirical relationship between the tropospheric delay and topography. And then it's implemented as a height correction. Another part is using the global atmospheric models from the software called PyAPS, developed by Roman Jolivet et al. And the third one is Geckos. It's similar to using global atmospheric models. It's from University of Newcastle University. And so basically all of them are supported. What you need to do is just specify the method here and with some corresponding options for each of the method. I believe for Geckos, the whole thing is not exactly automatic. So you will need to go to their website, as noted here, manually download all the Geckos products, and then just give the path of the Geckos product, and then MintPy will take care of the rest. So in here, we try to use the PyAPS method using the ERA5, which is one of the weather reanalysis model provided by ECMWF. It's basically a 4D tomography of the troposphere, which has the information for precipitation, pressure, and temperature, which can be used to predict the delay in the SAR image. So this is what it does. And for us, let's just run this. It will update the configuration file, and then we can just run it. So in this case, I already uploaded the calculated tropospheric delay in the staged data, so you don't need to download for yourself, and then you will just grab it and apply it directly. That's why you see it's pretty fast. There are similar to the DM or SF downloading. There are account set up for the global atmospheric models. Also, the information is on the GitHub in MintPy, and you will see that in the installation. So Forrest asked, in what scenarios do you think it's appropriate to use height correlation method? From my personal experience, I found that one useful better than PyAPS is when there is extreme topography. I found that sometimes the global atmospheric models is not working well on those cases. I think also because those cases don't have much satellite data or don't have much institute data there to constrain the model there. So in those cases, the height correlation is better. But of course, I would definitely recommend if you should try them all. For me, I would try them all to just see which one works for the best manually. The next one is remove ramps. This is a step to literally remove a linear ramp without physical meanings. So this is recommended if you study small scale deformation patterns like volcanoes, landslides, or city substance. If you're studying tectonics with large interseismic deformation or cold seismic deformation, then you should not do it. So in this case, we don't do it. The last one is a DM error or topographic residuals caused by the DM errors. We implemented this method by Harrich and Amelung in 2013. So what it literally does is trying to use the relationships between the topographic residual phase and the special perpendicular baseline time series, do a time series fitting, estimate the DM error, and then predict the topographic residuals and remove it. So we also want to do it in this case. Let's just add that into the template and run it. Okay, it's finished. Now let's check how the DM error looks like. It literally looks like this. So the last part is that the idea of this is that we're trying to estimate and remove all the possible noises that we could. And if there's still residuals that we cannot handle, if we cannot model them, or we don't know how to correct them, there's always something, right? So we want to have a graph of the noise level of those things too. So what this does is for each step, it will remove a ramp so that we only care about the short wavelength part for now. We're calculating an RMS of the residual phase. This part is the residual phase that does not include all the things that we just corrected, and it will also does not include a deformation model which we applied in the DM error steps. So by doing that, we grab in then with an RMS for one value, one RMS value for one acquisition will give us a value, give us an idea of how noisy or turbulence of that acquisition is. So the output of this step will be just a TXT file with an RMS value. Okay, that's a good question. The order of the corrections. Among all those orders of corrections, there are actually two categories. One of them is using external data, like PyAPS and solid earth tight. One of them is data dependent, like DM error. So I always recommend and should apply the data independent, the external corrections first, then apply the data dependent corrections, like DM error and deramps. And within each category, the order doesn't matter. So this is what the RMS looks like. In here, for every acquisition, we get an RMS value. It's probably to here. So we can basically see that with this graph, the high bars are acquisitions with relatively noisy dates. So then we got a 1D time series. So we can actually apply a simple standard outlier detection method to find the outliers. We think maybe there are some residual phase that are very strong, such as the ionosphere, if you're not corrected. and other very strong, sometimes very, very strong, occasionally tropospheric delays, also turbulence especially. And those days can be identified like this in an automatic fashion, and then remove it from the later on analysis. And also in this plot, there's this orange bar, which has the minimum RMS value, which we think is somehow the cleanest, the cleanest acquisitions, which we want to use it as a reference date. So which is this date here is saved as a TXT file here. So we can just use this date as a reference and change the reference date for all time series by running this cell. And note that when we change the reference date, we actually did not do anything. Changing the reference date will only give us a clean look of the time series only, because changing the reference date is literally equivalent to adding a constant to the displacement time series, right? We have a displacement time series. Changing the reference date is literally moving things upside down, but relatively, that's still the same thing. But in a map view, they will give us a clean look. So now we did all the estimation, we did all the corrections for noise, and then we did a noise evaluation to identify those noisy dates. So we will remove those noise dates and then redo the velocity estimation. Okay, it's done, and let's see. So these are our final velocity, and we can see that this part, the jump is gone because of the arm error correction. And I'm not sure it's more. Ideally, all those topography related, a lot of topography related troposphere should also be smaller. And in here we can again plot the transaction crossing the velocity. And yeah, so that's basically it. One last part for the validation. We can see from the previous steps that we can see that MintPy analysis is independent of the GPS observations. So this means that we could have two, if you have GPS on study areas, you can use that to validate the InSAR products independently. And this is what we do literally here. So what it does is MintPy has supported the GPS solution from the University of Nevada. If in the viewer PY, if you specify GPS related options, such as the ones here, it will grab the list of all the GPS and then download the GPS in your study area, calculate the displacement and velocity, and then plot on top of your GPS, on top of your InSAR velocity field. So you can see it's downloading that from UNR. Oh, the reference frame, that's a good question. So the reference frame for GPS or GNSS from Nevada is from the IGS 14. But InSAR is relative both in space and time. So what we did is we actually chosen the same reference to the GPS too. So the GPS we calculated here for comparison are also double referenced in the same reference in both space and time as InSAR, and which can be specified here as a ref GPS option. So all the GPS we plotted later on is referenced to this station, and this script will also re-reference the InSAR velocity to the pixel that includes this station as well. So this is how it looks like. And the GPS estimated velocity is plotted as the dots here, the color. So we can see that visually, the color matches. Where InSAR is red, GPS is red. When InSAR is green, GPS is green. And but we can also see there's some outliers here, right? You can see that here is redder, here is green, And on this part where inside there's no measurements, GPS has it, of course, because of InSAR decorrelation. So overall, it matches well. There are some of this might be due to some very localized effect from GPS. Another thing from visual, besides from visual, is we can just plot make a scatter plot, where here the x-axis are the InSAR velocity, the y-axis are the GNSS velocity, and we can see that they're matching pretty well, which gives us a good confidence that our InSAR measurement is reliable. We can see here, this here also plot some statistics for this plot. Here, the RMS is around less than 3 centimeter. The R square, the coefficient of determination. Is that right? That's a full name, R square. This value is very low. This is because of the outliers here. So if you actually recalculate without these outliers, this value will be high also. So that's it. Yeah. So basically, I think if you run your own data set, if you go to this step and you find a good correspondence or agreement between the two, then your InSAR results are good to go. There are a few other options. There are a few other functionalities in MintPy, but I think I will stop now and take some questions if you have.
It's odd that you have a negative R squared because it's squared,
Yes.
so it shouldn't be negative.
Oh, that's a good point. I think something's off in there. I did
It also
not,
looks low because the correlation looks good. So really, that's the
Yeah.
square of the correlation coefficient. So that's all.
Oh, so okay, I remember that now. Yes. First, the correlation low. It is because of the outliers. You can see here, as GPS has some very localized processes here, and here. This is very red. So this scatter plot does not plot everything because of the bounding box on the XY axis. The R square can be negative. It can be negatively correlated with each other too. So that's, I think the calculation is right. It's just the low value. It is literally because of the several outliers in the GPS, and that makes just the coefficient very low.
Oh, yeah, that's right. Yes. Nice. So you cropped the figure basically.
Yes, cropped the figure. Yeah, it's an automatic thing. So I literally just grab the range, the data range from the InSAR and use that as the bounding. Otherwise the whole bounding box will looks very wide and everything here will be just clustered into a dot or something. Let's see, is there more questions?
So that comparison to GPS is a really nice feature of MintPy. You should totally try that out.
Yeah, it's nice details of all this calculation. Once it's done, it will write all these calculations into a CSV file, so you can actually just reuse them for your own purpose if you want. And the GPS shows the information of local movement, such as building, and so S-Bus does not. Yeah, totally, definitely. The difference is a lot of times between InSAR and GPS, and Garrick and friends, please feel free to jump in also. The difference is a lot of times because of in GPS, the whole thing is mounted into a rock underneath, and sometimes so the things that GPS measures are not exactly the deformation right on the ground surface, which is what InSAR measures. So that causes in a few scenarios cause the differences between the two.
Yeah, I guess depending on what you're looking at, the comparison to GPS is maybe straightforward or not. say one of the things that we like to do is we look at permafrost a lot, where we try to sort of understand the subsidence and heave of the permafrost underlain areas throughout the seasons. There, the comparison to GPS is not as straightforward, because the GPS sensors are usually installed in a way to avoid the active layer freeze and thaw processes. There is often a mismatch between the GPS and the deformation InSAR sees. So it can be in some areas that there is a difference because of the two data sets seeing different physical processes. But here, mostly, I think it should be fine. It could be that there is localized, the way the GPS sensor is placed causes an issue. I think there are some sensors where that is known. I'm not sure, Gareth, if you know anything about those specific ones.
Not in this. I mean, yes, that they exist and they are documented often. You can actually, for UNAVCO stations particularly, you can go and visit they have web pages dedicated to them with field photos, and sometimes you can find out what it is that's going on just from those. But yeah, Yunjin in general is right that the people who install GPS stations pride themselves on not picking sites that are not susceptible to some of the things that InSAR measures very easily.
Yeah, Hane has a great question. So what we showed here in this notebook, to me, always the real useful thing is the final displacement time series, not the velocity, because we know that we only apply a very simple model. So to me, the InSAR displacement time series is like the GPS daily solution to me. And I always start my analysis from there. And there are more efforts in both community. A lot of people are actually spend a lot of time on the time functions, such as the group in Caltech also. And we are also adding more time function capabilities into MintPy too, but it's not integrated into this routine workflow or applications here yet. But in some MintPy scripts, if you're getting more familiar with it, you will see some capabilities there too. And so in that sense, I would think it's always fair to compare GPS time series with InSAR time series, not the estimation of the time functions.
There's a reference GPS site or reference question. Do you see it in the chat?
Yeah. Yeah. So how do you go find a reference GPS to your entry? So what would you go? Yeah. So what I did for this study is we previously select a reference pixel here. So for this data set, I just choose a reference pixel close to it, a reference GPS station close to it. And if you go for other applications, and also another reason for we choose a reference pixel right here for this data set also is this data set, this pixel is close to the fault boundaries, close to the faults. And we know that because of the spatially correlated noise, when things are closer to the reference point, they have less noise. So that's why we choose the reference point here, near to the fault, and the GPS just near to the reference point. And for other studies, if you have volcanoes, of course, you want to choose a reference GPS away from the deformed areas. And Brent Minchu also said for the glaciers, sometimes you want to choose stable mountains out of the ice stream or shelf, so that you can have so that you can measure the relative deformation on the target of interest. For Muhammad's question, the two are the same here. in our processing, we choose a reference point around here. But for this plot's sake, the code will actually reference the InSAR to this point also, so that they are consistent.
So that's a post-processing step that's applied here by selecting a reference site. A reference.
That's done on the fly by view the PY.
Okay.
So yeah, it says here, there's also a message.
Mhm.
Yeah.
So in theory, if the inversion was done without error, the switching of reference points is simply a shift.
Right. Exactly.
So you can, pick different reference sites, and it will shift the time series accordingly, assuming that there are no gross errors in the processing.
Right. So yeah, that's why in the MintPy, in all the visualization scripts, there's always a reference point option to allow you to change reference point for visualization or for your information grabbing, because it doesn't really matter. If your inversion did it right, if your initial reference point selection is appropriate, it doesn't have to be always perfect, right? You might just change your mind at the last minute after the processing. I don't think I quite understand your question, Parvis. Since GPS values are absolute, to use one station as reference. Oh, so yeah, sorry, here I should be more clear. When we say reference here, we did not tie InSAR to GPS. We are actually tied both InSAR and GPS at this point to 0.
And I guess maybe the question also hints at, so right now we are talking about a single point or a single reference area. Does MintPy have options for doing a network-based referencing?
What do you mean network-based?
Well, where you basically would pick not just one point, but maybe several locations for referencing, and would do some sort of a least squares fit.
Oh, yeah. Good question. It does not. I'm not very sure about the impact of that. That is not the area base, right? It's still, you're still talking about multiple referencing, maybe spanning all
Right.
the scene.
Yeah.
I see a couple of papers from about that, but I haven't checked carefully yet. So maybe Harish want to jump in for more comments, but
yeah, I'll just add to that, Franz, that has been on purpose that we don't do it. We have been hesitant. We would like to keep the GPS and InSAR as independent as possible, as Yunjun showed. So, and we would like to keep doing that. As you mentioned yourself, the two sometimes observe different things, and we want to understand that more. So we don't want to force them to fit to each other. I think the end users can do that on their own if they want to.
There's one more question by Carolina, and then maybe after that we should probably go to a break because we have one more.
Yeah.
About 20 minutes behind, I think. Do you see the question?
Yeah. Yeah, so the question is, could I divide the area into sub areas and use a reference point for each and then merge the result? There are actually papers doing that. There's papers recently come out last year, which actually literally do that. It's from Kam et al. I believe it's working with John Lu from SMU. I think that one is useful if you have multiple area or signal of interest in your data set, and you don't really care about the long scale information. So you don't really care about the long special reference deformation, such as tectonic ones. If you only care about a small deformation, it's fine to use for a small area. For each of the small area, use a local reference point, and you do can or second together, of course. But of course, in that map, you don't really have good. You don't really have information on a long spatial reference. But if you're aware of that, and that is not your interest, it's fine, definitely.
Great. Thank you, Yunjun. That was fascinating. I hope you all enjoyed, what nowadays we can do with these tools, and also it's fantastic that Yunjun and Haresh and the entire team didn't just develop this, but made this freely available. This is, I think, one of the very few free and open resources for this kind of work. So it's really, really great to have these resources nowadays. I think we have one more segment to go before the end of this course, which is intro for preparing data for stack processing. We are behind, but I would suggest maybe that we do take a short break to let people shake up out their legs, maybe for 5 minutes. Is that fair?
Yeah.
And then go on. Yep. So see you back in 5 for the last element of this course.
See you.
All right. So can we start, Franz, or we should wait?
I think before we start, we should have one last reminder about the surveys. Hillary is on the call. Maybe she can make the pitch herself.
Okay, so let me stop sharing then.
Hi, everyone. Thank you so much. Those of you who did the pre-survey. The post-survey, I'm going to post in the chat again, just for your convenience, but it's also at the end of your syllabus. It shouldn't take you too long. And as Dr. Rosen said this morning, we really appreciate your feedback on this. This is a funded project by NASA, and they're looking to take these modules and make them flexible so that people can use them from a semester-long course to a workshop like you've participated in, and make them available to people like yourselves who might be teaching others. So we really would appreciate your feedback. I also do a lot of analysis on the changes in your knowledge based on the course, and the team takes this very seriously. Last summer, there were probably people had showed huge improvements on 2/3 of the questions and not so much on the last third. So there were a lot of adjustments to the modules, to the notebooks, and to the lectures to try to improve the instruction and therefore improve the outcomes. So we hope you'll take time to do that. I will be bugging you off and on if you have any questions about it, or can't find the link. I will put it, I think I'll go ahead and put it in the grade book, and you can see there that you completed the pre-survey, and then every day I'll update it so you can check to see if your post-survey was received. So thank you so much, and thanks for attending the course.
Thanks, Hillary. All right, Haresh is going to teach us about stack processing. Which is another way that you can use what you've learned in this course and then feed it all into MintPy.
All right. Thank you. And I hope everybody had a great week. And hopefully you are not too tired. So I hope so far you know that there are ways to process the pairs of the data within ISCE2. And with ARIA tools, you probably saw that ARIA took ISCE2 and basically runs TOPS app on many pairs. So there are stacks of data, and then ARIA tools takes them and stitches them together or makes a stack that can go then to MintPy. And that's what Yunjun talked about today. But the other way would be to just process data with ISCE and import it to MintPy or to other time series packages if you have. So basically, that's what we mean by stack processing. Why stack processing? Basically, if you want to do time series analysis, as Yunjun just showed, you need many interferograms. And that's mainly to beat down noise and to get to very small signals. If you look at those individual interferograms over the Bay Area that Yunjun showed in the MintPy example, you won't see usually that creep signal of the Hayward fault, or you don't see even the tectonic signal across the plate boundary. So you need to do time series analysis to reduce the mainly residual atmospheric noise and get to that small movements that you are interested in. So, okay, so you need a stack. You can either run pairs, many pairs, which you could run TOPS app or StreetMap app many times, as many as you want. And then, but you have to do on your own, you have to crop them and make sure that they are on the same grid, and then feed them to MintPy. Or no, just use the stack processors to basically, at the very beginning, align the stacks of SLCs. So instead of co-registering 2 SLCs of the reference and secondary, then you have whatever SLC you have, hundreds, and you can align them together at the very beginning. Then naturally, all the interferograms and other products are already on the same grid. So if you do pairwise processing, one drawback is really you have to run the RDR2GEO, the transformation, the topo module basically, which transforms the radar coordinates to geo coordinates many times, as many interferograms that you have. However, if you run the stack processor, then that step, which probably by now you felt that that's an expensive step in our workflow, we run that once. So that's a significant processing reason for that. But also the accuracy of the alignment and keeping the consistency within the entire stack definitely is better when you align the entire stack at the very beginning at the SLC level. And that reduces the processing errors, which at the very end could contribute to that non-closureness of the stacks that Yunjun talked about. We have some contributed stack processors to ISCE2. We have 3 of them: the StreetMap stack processor, the TOPS stack processor, and the ILO stack processor, which really the new part of it is for ScanSAR, which was contributed. That one's contributed by our colleague Shunran Liang. And the stack processors are so you saw the you had now experienced hopefully with the pair processing, and you saw that as soon as you go with your own data set, even for one pair, there are issues usually, and you have to deal with this. So the stack processor is really designed for advanced users. I strongly encourage those who feel comfortable with the basics of the interferometry, the processing steps in ISCE2 for pairs, and they are comfortable with Linux and with Python programming. Then try the stack processing, because there might be issues, and these are really contributions from the either ISCE developers or community developers, and we appreciate more contribution. But people who usually use these the stack processor should be comfortable with Python and Linux. So there are a couple of them, as I mentioned. There is the street map stack processor. Here is a workflow from a publication a few years ago. Then in the street map stack processor is, as the name suggests, it's really for processing a stack of street map data. So that could be from different sensors, whatever ISCE2 supports right now. And there is a block here in this diagram that basically is doing that geometrical co-registration and also some improvements of the co-registration, basically that cascade co-registration and refinement with the cross correlation. There is another block that is more for the ionosphere if somebody wants to estimate ionospheric phase, and that's more related to the split spectrum and resampling. So by end of here, we have a stack of SLCs. And if you want the ionosphere, we should have a stack of subband SLCs as well. And then you will get a stack of interferograms and the even some tools for inversion of the ionospheric phase to get to a time series. Here is an example that from a publication a few years ago that we used basically that tool. We developed that tool for this purpose actually at that time. That a lot of ALOS data in Chile, we had many pairs, and we formed the pair interferograms using the stack processor, as well as the ionospheric phase, and then inverted with, I believe now the same things, yeah, with MintPy. You can get a time series of the interferometric phase without corrections, and then with MintPy you can put in also probably ionospheric phase and get the same time series of ionospheric phase. And then that's the difference, which shows you how this was L-band data, so heavily affected by ionosphere in equatorial belts, which is expected. And then here is the workflow for the TOPS stack processor. For the TOPS data, we start with geometry, and we usually have the one reference, similar for the street map as well. For any stack processing, we have one reference image, and we look at the overlaps of the entire stack, not only one pair, but the entire stack, and we come up with the misregistrations of the misregistration time series, basically. And from there, then we get back to the full burst, and very, very similar to what was in TOPS app, but now for a stack. And we get to the resampled secondary burst, and finally to burst by burst interferograms, and then we merge them, and we get the rest is just filtering, unwrapping, geocoding if needed. The resources are really all in public GitHub of ISCE2. If you look at the country folder, you will see that there is a subfolder stack, and then there is street map stack, top stack, and ALOS stack, which has basically different stack processors. To get the stack processor in OpenSAR lab, all you need to do really is to open a terminal, activate your UNAFCO environment with this command, conda activate UNAFCO, and then add the path to the stack processor that you want, in this case TOPS, to your path environment. Basically running only this command, the exact same command, if you copy paste to your terminal, then to make sure that everything worked fine, you can just check with stacksentinel.py -- help. If you don't do this, you won't have access to this script. But after doing these few simple steps, you have stacksentinel.py. And if you have your own machine or your cluster, and you have installed ISCE2 with conda, then exact same thing should work, except that, of course, it's your machine, then the environment might have a different name. Just be careful with that. And then, yeah, go ahead and do this simple adding the path to your path variable, and it should work. Similarly, for the street map, exactly the same thing. but you need to replace the TOPS stack with strip map stack. And then the command for strip map would be stack strip map.py. And finally, for the LO stack, again, just replace with LO stack. And you will see that you should be able to have this command. And here are the references for whatever I explained. But in the GitHub, there is a very detailed README of each of the stack processors that you can go step by step. I'll share, and 1 second I will show you what really exists in the GitHub.
There are some questions about where you put that presentation.
Oh, I sent it to Paul. Paul is gonna add it to the repository, so it should be available to you all
When Paul gets done with his meeting. So
yeah.
I actually just restarted my server just now, and then it actually showed up on the
So
5.3 there in the PDF. If you click it, it should show up on browser. If there's a problem, maybe you could try to download them to your local computer and see it.
yeah. Okay, thanks, Yunjun. So Paul already added to the repo, and it's already available to you. So if you look at
excellent.
So if you go to the GitHub of the ISCE2, in the contrib directory, there is stack, and in the stack there is a README, a general README, and in each of them, let's take a look at the top stack, for example. There is a README that recently, I think Yunjun made it even cleaner, and you see that there is a really very good instruction of the step-by-step processing of with the stack processor. Step 1, do make your directory and prepare your DM and download your Sentinel-1 data to the SLC folder, and then run on stack sentinel.py command. The main difference with the pair processing is that this command is gonna just write a lot of shell scripts that are gonna be run in parallel. So Yunjun is gonna demo the exact same thing shortly, so I'm not gonna go to the details, but then just keep in mind whatever he's gonna demo, actually the instruction is on the GitHub in the README for each of the stack processor. Once you run this command, which basically, as you see, you just say, where is the SLC, where is the DM, where is the orbit, and what bounding box do you want, and what workflow do you want? Because we have different workflows. We have SLC workflows, which just creates a co-register stack of SLC. If somebody want to do PS analysis, you just want SLC aligned. And if somebody wants interferograms for MintPy, then you want to choose workflow in interferograms, and so on. So once these are these run, and that creates, there are many more options. You can take a look at the details, but once these run files are created, then inside each run file, there are many commands that needs to be run in parallel. You can run them to process one by one to get to the stack. So that's all I have, and I'll let Yunjun to show you a demo of what it can do.
Okay, so this is a demo for the stack processor. Just trying to make them bigger. So we, as Harris just said, besides the normal ISCE installation, you need an extra step. So in here, this is just one of my BIOS, one of my alias to just load the ISCE. My ISCE is loaded in here. And then I need an extra step to load the iStack processor by just setting up the path. And by just doing this is exactly the replica on the nodes on GitHub. So you could just, so you don't need to worry that you will forget it. So after doing that, then I will have the stack processor, which is the main script is called stack sentinel ready. If you just type -h to check the help, you will see that it has several options. Since it's a stack processor, I definitely recommend you to read all of these options so that you're familiar with capability. In this demo, I will just show one example with the example workflow of interferograms, which will generate a stack of interferograms ready to be ingested into MintPy using Sentinel, of course. And here, if I just go to one of the directories, in this directory, what I have is I have two folders. In the SLC folder, these are all the Sentinel-1 data I downloaded from ASF using the ASF bulk downloading command. And then there's another folder called orbits, which I pre-downloaded some of them so that I don't take time. So what I now do is literally following the workflow outlined in the README file on GitHub that you just see. So in here, the first step is just to create a DEM. So I create a DEM folder. I then go to the DEM folder. Then I run a DEM.py command to download and generate the DEM. This is -a for action to stitch, which I will download each grid of the DEM and then stitch them into one DEM file with a bounding box. This bounding box is this bounding box needs to be in the integer in the order of south, north, west, east. And then I know this area pretty well. So this I choose always be very generous, give a large bounding box to make sure your DEM always cover the whole static area. Then with R for report, with S for source. Source is, sorry, let me just show you the DEM, what the help is. These are the DEM. So all the scripts, if you just type -h, it will give you the help message. And here there's some examples. Just now, these are the things that I typed. The source is -s. And with one, this is trying to download the SRTM DEM, which one is equals to the one arc second, and 3 to the arc 3 arc second. One arc second is around 30 meters. And then with C for correcting the DEM from geoid into the ellipsoid. It's a reference frame thing, and the ellipsoid is always what we want to use for InSAR processing. And in this case, I'm trying to do some analysis on Sandra's fault here. And we know it's a coastal area. So on some coastal areas, there's some tiles missing. So I need to do some filling if the tile is missing with a filling value of 0. So with here, it will just automatically search and download the DEM from the Earth data using your Earth data account. Still the same thing as you download from ASF. It will download all the grids one by one, and later on, it will just stitch them into one big DEM file. It'll take a few seconds. Okay, so you see this part, what is reported as fail is because of the missing tiles on water. There's no SRTM there. So that's when the field value, what we just specified, is filled in. Okay, so let's just check the folder. It downloaded those files and then created this one DM file. And then there's another one with a suffix of WGS84. These are the DM file corrected from geoid to ellipsoid. And these are the DM files we want to use for the InSAR processing, including the stack processing. So now let's go out to the root directory and start to run the stack sentinel. Again, you can always check the help there. So in here, is sentinel1? I checked my data. I want to use the whole 3 subswats. So I specify the subswats number here, 1, 2, 3, with a bounding box again. And then this bounding box will be the bounding box of your area of interest. And remember, when you search on the ASF, you will also have a bounding box if you use the geographic search. So usually I use the exact same bounding box here and there to make sure that all my data set in my area of interest are for surely downloaded. So in here, just from Google Earth, I know these are my area of interest in more detailed, light and long. So this is still in the south, north, west, and east order. Then I want to specify a reference date. The reference date, you can check your SLC, the state there. So in here, I want to choose a reference date on 2019, and I use a co-registration. You remember co-registration, there is 2 methods, either use ESD, the nested ESD, or geometry. Here, I just use geometry. This is my personal favorite, which is I'm using almost all the time and haven't given me problems. And I use a workflow, it's the interferogram workflow with a number of connections. These are the number of connections that we want to generate interferograms. With one SLC, you generated this number. For example, I choose 3. I will generate 3 nearest pairs to form the interferograms, and then specify an Asmus look number with a 5 in Asmus and the range of 15. With a sentinel1, a ratio of 1 to 3 give us a relatively square pixel size in the output. You can reduce it or increase it to determine your resolution of your output interferograms. Then give us set the SLC directory and then a DM, which is what we just generated here. Then with 2 more things. One is the auxiliary files. These are the auxiliary calibration files from Sentinel-1, which we just need to specify a directory. We don't need to do anything, just create the directory, and then I just create one directory, which I almost never use and touch. I just create it there and then specify there. Then the code will just download whatever is needed to that directory. I also specify our orbit directory to save all the orbital data downloaded also. And that's it.
Yunjun, you have a typo at the very beginning, SWAT num. You have a C, CH, yeah, remove C.
Oh, thank you.
Looking at watches, swatch. There's a question about the reference date.
Yeah, the reference date, I'll get to that in a minute. Let's just here first check. So you see what it's doing. After we run this script, it will check the orbit folder and then downloading orbit data if it's not existed. And you can see that most of them, they existed. I do it on purpose to save time, but I do delete some of them. So they are downloading them automatically. You don't need to worry about that. Just run it. After it downloads all the orbits, now you also have the SLCs. You will have a brief report. These SLCs includes 93 dates. And with the date, this is the center of the things in the south, in the south and north direction. And then with the report, you will see that the overlapping region among all the dates are these here. So you need to make sure that your input bounding box is included within these dates to make sure you don't have data missing. And these are reported also. You can see all dates, that's this much. And we have the same number covering the bounding box we specified. And it says all the SRCs will be co-registered only to this date. And this is a reference date for co-registration only. The interferograms are still all formed in the small baseline pairs. And then after that, it will show that it's a geometry constellation with interferogram, the two most important configuration. And then it will write its few round files that we just seen in the GitHub. So to the question about the reference date, if you don't set it up, it was set by default to the first date. And personally, I always like to set it up because in Sentinel-1, the first dates are in 2014 and 15. And we know that now on those years, there's ionosphere. So I set a date usually from my personal experience, I set it to a later ones around 2018, 19. And let's now check again what files we have. So besides the DEM, orbits, and SRC, we have two more folders. One is a round file folder. If we just check that, these are literally these few round files, and each of them has basically a command there. If you check one of them, it's the second step. Oops, I need to go into the folder. Here, you will see that for each date, it will have this one command, and same thing repeated for all dates. In a similar fashion, if you look at the later stage, for example, the unwrap, which will have interferograms, so it will have one line of command for one interferograms. So this fashion make it very easy. If you're familiar with HPC or high performance computing, you can submit each line into a separate job, and then you can run all those operations for each step simultaneously. And so it's very good for large scale and automatic processing. And another folder here is a configuration folder. And in this configuration folder, it actually saves all the parameters set up for each of the steps. For example, here this is the unwrap. In this unwrap, we see the input, this file, the output are these two files, and these are the detailed configurations for unwrapping steps. And you have the same thing for all steps in every interferogram and every acquisitions. And that's why you see it's a folder with a lot of files. So now let's go back to the root directory, and basically that's it. So what you need to do to run these files is literally go to the run file directory, run every single one of them one by one. And you can do that just by, for example, type that to run it, or just to make it executable. And then run that in this fashion. Or to me, my personal favorite is another script called run the py, which is a script to do all these things. We said, for example, we want to, for example, for this one, there's a lot of fun. For unwrapping, there's maybe hundreds of interferograms. So what I do is, actually for this step, I feed this file to it, and then you can see from the help, I give, for example, 100 processors. If I have 100 CPUs, I'll just run it like this. Then it will actually just submit them or run them in 100 CPUs in parallel. So for me personally, I run all these interferograms with this command style and run them one by one in a sequential order, and then you get your results. That's it.
Just thank you, Yunjun. That was really great demo.
So sorry, before And let me just show one more thing.
Can I comment on your -P100?
Yes.
Before you
Yes.
show one more thing. So the number of processors, you have to be careful and you should know what are you doing. There are processing steps that are multi-threaded, and they are already trying to use multiple cores that you have. In this case that Yunjun showed unwrap, that makes total sense. If you have 100 processors, unwrapping is single threaded, so each of them could run on one processor if you have enough memory. Otherwise, if the processing step like topo is multi-threaded, then you have to make a choice there, how many jobs you want to run. So there is really more knowledge that's needed on the basics of the programming and computer science to be able to efficiently run these things.
Yeah, thank you. That's very important. So I will have one example to show you how all this looks like after you finished your processing. This is the exact same data set. After you finished, ignore some of them because I removed some of them because the file is huge. So after processing, I removed a lot of intermediate files and saved only the final results. So in here, I'll just show you the final results. For top stack, for example, the final results is in this folder called merged, because we have merged bursts and subsources. And if you go to merged, you will see the merged geometry files. Sorry, this is old. I apologize. This should be geometry reference. This is an old processing. They are merged SLCs. So all these SLCs, if you go deeper into one of them, you will see these two files. It's a VRT, is a virtual file to save space. So you will have the fully co-registered SLC, all consistent with each other among these folders. If you want to do your own processing, for more advanced users, and for interference workflow, there will be an interference folder under the merged directory, and they have all the pairs that we just selected. And among the pairs, if you check one of them, it will have this called filtered fine decor, which is basically the coherence you want to fit into MintPy, and the filtered fine.unw, the unwrapped interference you want to fit in MintPy, plus the kinetic component. Yeah, so that's it. I do have a quick demo if people want to ask questions, but I also do have a quick demo for StreetMap stack if you think it's useful.
Yunjun, do you have on your list also to show the configuration of MintPy where you directly input the data from the stack processor?
Right, yes. Let me just go here. In MintPy, if you go on GitHub, in MintPy here, if you go to the top of GitHub, there's a documentation website. Just click there. Then it will bring you to a documentation. In here, a very useful thing is this here called the example directory structure. It will put a list, example of all the processors MintPy currently supported. For example, in here, let's first go back to ARIA. These are the directory that if you use ARIA with MintPy, these are the directory of what it should look like, and the corresponding template options for the input parts. This is what we did for the notebook earlier. And if we go to check the IS top stack, these are the same thing I just showed before. And these are the input options for this specific data set, this specific type of processors for MintPy. For example, here you need to specify the metadata, which is a MXML file, the baseline directory. And here, these are the files that we just shown, the field find.core. You need to specify that with a white card or with a star here. so that the code will use this wildcard pattern and search to grab all the files that is needed. Similar thing for the coherence and the kinetic components, but for geometry files, you don't need to put the star here, because for geometry files, we only need one copy of that for one stack. And you can find the similar example directories with the input options for all the processors that is currently supported as a reference. Yeah, that's it.
Yunjun, there is a question in the chat about can they provide their own list of interferograms? They might not want the short temporal baseline. Is that the question from Beatrice, I guess?
Well, it's like, for example, when you are using small baselines, but you also want a few interferograms that have longer temporal baselines just to keep track of everything, then how can you do it? Because I've tried to use ISCE before, and that was always an issue that I couldn't figure out how to provide, say, a few more interferograms that I wanted, and that ISCE was not deciding to calculate by itself.
In command line, the top stack does not support that in the command line inputs. In the code, it should definitely doable. I think it's just currently not implemented. I think if someone who is familiar with Python, they can easily modify that, add 2 more options to generate those pairs. If you have a reference list of dates, it's also currently not supported. I think you also need to somehow to modify the code in the stack sentinel.py in that script to modify that to make it support. But it's really, I think it's really a trivial thing to do if people are familiar with it. I think just a lot of us developers are very busy with a lot of other stuff, so they cannot do everything what everybody wants.
Yeah, thank you.
So I guess I could add a few things in. If we are processing into StreetMap stack is the similar fashion. Just follow the workflow described in the GitHub README, and that's it.
Oh, there's a good question about contributing to ISCE. I don't know who
Maybe Harris want to comment on that?
Maybe.
Yeah, definitely you can contribute to ISCE. It's on public GitHub. So yeah, we appreciate, and definitely we welcome contribution.
The stack processor is a contributed code, right?
That's true. Yeah, a couple of us, even when we were not part of the team, we contributed.
So I guess in the previous session, the homework for today is that in the MintPy notebook, I use the same dataset, but play with more options in your, especially in the weighting, in the time series error corrections, and also so that's the homework for that. And you also see that from the syllabus, you should supposed to, after getting cleaned up displacement time series from MintPy, you could save that into velocities or displacements for modeling. And if you want, you could also combine that together with everything you have learned through this course. So do the processing in the time series part, clean out the time series, using the time series for modeling, and do the modeling. And on the last part of the MintPy notebook, it's safeguarded. So there's some other functionalities that is not covered in the main small baseline app application. So I do highly recommend you to go through that. That's a lot of useful utility tools there.
So that sort of gets us to the end of this course. I think we have a couple of more things to say. One of them is the post-course survey that was posted again by Hillary. So please go in and do that survey. Another piece is, right now you will have another week worth of time to finish your work using the OpenSAR lab. So the OpenSAR lab will stay, this installation of the OpenSAR lab will stay available for another week for you. We did say that there is sort of an end of life option, which is sort of a Dockerized version of what you see on the OpenSAR lab to be deployable to your local machine. I do have Alex and Eric on. Are you guys still there?
Yes, we're here.
Talk a little bit about what that means and how it can be deployed and where you can find it.
Great. So yeah, we've built Docker images for Windows, Linux systems, and x86 Macs. Currently, we can't support Macs running the new Apple Silicon M1 chips. They're just all of the packages needed aren't quite there yet, but those other systems are supported. And here I'll share my screen if I can. All right, so we're going to put this this repository. We're gonna create a repository in ASF OpenSAR Lab, in the ASF OpenSAR Lab org. I know there had been some talk about actually adding this to GeoSync, but part of the process is cloning the GeoSync repo, and so we would end up with a repo cloned inside of itself, which could lead to some issues. So we're just
like
going
the
to
Inception movie. It's like
what's that?
A repo and a repo and a repo. It's
Yeah,
it's
exactly. And we don't want to go there. So so we're just going to put it in the ASF OpenSAR Lab org, and so we'll provide a link shortly in the Slack channel for how you can access that. And so when you get there, there'll be a README sort of walking you through the instructions that you need to follow. So for Windows, you have to set up WSL2, which is the Windows subsystem for Linux. It basically runs a Linux shell in your on your Windows machine, and so that will only work for Windows 10 and higher. You also have to have Docker installed, and so we've provided some links to installation instructions for different systems here. And of course, you also have to have Git installed, and so there are also some links for that. And then this instruction here will actually change. You'll be cloning in the repo, from ASF OpenSAR Lab, and then all you have to do is move into that that directory, and there's a home directory here which will end up getting mounted in the container where all of this will be running. So if you have other files, other notebooks that you'd like to appear in your and to appear as accessible in your container, you can just, once you've got the repo cloned, you can just copy those into this home directory here, and they'll be available for you when you launch the notebooks. And then you just run this little script here, build start UNAVCO container, and this just has a couple simple commands: one that builds the container, or the image rather, and then one that runs that image in a Docker container. And once that has completed, that does take some time. Just to mention, it can take about a half an hour to build the environment, the Conda environment. It's quite large. But once that's completed, you will see a screen something like this with some URLs at the bottom. And if you just open one of these URLs in your browser, then you'll be in. And so actually, Rui, are you on the line here as well?
Yes, I am.
Great. So so maybe I'll stop sharing, and then you can show what that would look like. Rui has it built on his machine, so he can show you what
Okay.
that will look like on your machine.
Okay, let me share that. Oh, here it is. Can everyone see my screen?
Yes, we can.
Okay, perfect. So this is what it looks like once you build them. And this is, right now I'm in a geosync repository, but like at the top level, you should see three different directories, or sorry, 2 directories and 1 log file. And just like the geosync directory that I was in previously, and here's
so,
UNAVCO, and here's all the contents that's relevant.
And so if you have, if you've made changes to notebooks in this, in the UNAVCO 2021 directory in your OpenSAR Lab account, you may want to download those separately and then copy those into that home directory so that they're accessible to you in your Docker container. Because once the UNAVCO deployment of OpenSAR Lab gets destroyed, all of that will be lost as well. So you should, if you have things you'd like to save, you should definitely download those, before the end of next week. And then, Rui, maybe you can just show how you can create a new notebook using the UNAVCO Conda environment there.
Okay, so you can go to like this new tab, and you can click NAVCO and make a new notebook. So you can do something like, if you want, just for example, you can just hello world, and you can run hello like hello world, or any like Python scripts. You can also run various bash scripts with using exclamation mark, and you can run every JavaScript function using like the %2 sign.
So maybe if you could just run exclamation point which Python, then we can just show that it's,
okay, that's a good one. Okay.
Yeah, just because that shows that you are in fact using the the kernel that's part of the UNAVCO environment there. And so so once you're done here, maybe I'll start sharing again, Rui, if you can.
Okay.
Okay, so so once you're ready to quit out of to stop your session, you just hit Control-C, or if you're on a Mac, yeah, the other Control-C twice, and then the next time that you want to start it up again, you just rerun that same script, and so if you've never installed if you've never built the image before, the first time it will take a half an hour or so to build that UNAVCO Conda environment. But in subsequent runs of the container, it just checks to see if there are any updates to be made, and if there are, then it updates that environment. Otherwise, it just runs it as is, and so that that time is reduced to just a couple minutes. It does take a couple minutes to start up the container, though, and so. We've recommended a specific command for running that script, which will tee all of the output to a log file. So if you did run into trouble when you were running this, you know, and if you reach out for support, if you just send us that log file that gets created, you know, along with your question, then that can really help us figure out what's going wrong on your specific system. Docker files are or containers are a little tricky to run on multiple platforms. But we did get it tested on Linux and Windows, and we didn't have access to an x86 Mac, but we expect it to run the same as it would on a Linux system.
And so this gives you everything you need. It comes, of course, with the notebooks that we looked at, but it also comes with the installation of ICE in that environment, and with MintPy and the ARIA tools components that we all use today. So it's a fully contained setup that you can then go and run with to do, you know, either rerun the notebooks that are there or build your own workflows within the environment. And so Docker is not easy so it may not come as natural to everybody to set this up. So we'll provide some information in the Slack channel where you can find all the information to get started. And I encourage you to reach out, first of all, to each other. Some of you have experience with Docker, other ones do not. So hopefully a lot of the questions that you may run into may resolve itself by just communicating amongst each other, as you have done throughout the course. And we'll check that regularly also to sort of help you with setting this up. So hopefully it's going to be useful and successfully deployed for you to keep going with this kind of work.
So Franz,
yes.
I'd like to point out that, just a reminder for everyone, you need a good internet connection because the image can be 5 to 8 gigs in size. And so if you have slow internet connection, it'll take you all day and all night to download stuff. Not fun, which is kind of unfortunate. But so you also probably should have at least 8 gigs of RAM on your computer to really run these things too. You need a nice sized computer. So I'm just pointing this out, that the Docker file is not designed for the faint of heart. You have to have a good machine to do it and a good internet connection. So.
Okay.
Do you want to say a few words on the assignment and timeline for that, or the credits it was sent?
Yes. So I think the timeline for the assignments, they are listed in the syllabus. So these are expected cutoff for project submissions. That's listed throughout the syllabus in several places. So please try to stick to that. What else is there to say? Hillary, do you have other notes on sort of the completion of the course for people that requested certificates or credits?
I saw an email from Melissa today that said that people could still sign up for credit up to September 1st, which is next Wednesday. So if you're thinking you want to do that, you can be in touch with Melissa from UNEFCO because they'll be handling that. And for the certificates, we expect you to do the homeworks and because then, it shows real evidence of effort and learning, and also the pre-post surveys, and they'll be open through the 3rd. If you have some kind of emergency, let us know and we'll give you an extension, but we need to do a report on the results and move on to our next task. So we'd appreciate you completing everything by next Friday. It's next Friday, the 3rd, Mohammed. Did I
make
that clear? Okay.
Yeah, it's in a week. Not today, but in a week.
Yeah, in a week.
Well, maybe that wraps it up. Is that true? Do we have anything else to say?
So, yeah.
And so with that, maybe we let you all go, and want to thank all of you for sticking it out all the way to the bitter end. It was a very long, demanding course for all of you. I know that we threw a lot of information at you. Maybe a reminder, if you go to the syllabus, all the sessions were recorded, and there is in the syllabus on the early pages a link to a YouTube what do you call
Channel.
it, YouTube channel that sort of where all the individual lessons and lectures are listed. So all of this is available and will remain available. And so with that, thank you very much for your time, and I hope you enjoyed it and walked away with a little more knowledge than you came in.
And that you'll share it widely.
And just a special word to the UNAVCO staff and the ASF staff behind the scenes who've been making all this happen. And to all of our full-time and part-time instructors who got, many of whom got roped in by their bosses. Without their help, we would not have been able to do any of this.
Yeah, I'm glad that Alex could come on. So Alex, thank you for the ASF, for the OpenSAR Lab team. And Rui is brand new to the OpenSAR Lab team. Glad to be able to show your face. So, okay. You guys have a good weekend. Stay in touch.